Hello, everybody, and good morning, good afternoon, and good evening, whichever time you are, where you are. Welcome to the first international workshop on hazard perception in intelligent vehicles, and a warm welcome on behalf of the organizing committee. I am Ardhendu Behera, and I wish you all a very happy, healthy, and prosperous new year. Just to update a few things as before I hand over to my co-organizers to introduce keynote speaker, a few things about that. Originally, we planned this workshop to be held in Hawaii as a hybrid option because of the current situations about this Omicron and travel restrictions. We've decided to do fully virtual, and therefore I thank you for all of your support to make it happen. And all of us, we wish to for the virtual virtual presentations, meeting, etc. All of you know it's a very simple things. Is my slide is visible to all of you? Just to clarify that I'm.
Yes.
Yeah. Okay. So just simple things. Please mute yourself when not presenting, and share your presentation using the share buttons, as well as if you ask questions, I think you can use the chat options. One of the co-organizers or organizers going to read out those questions to presenter. And just to remind you that all presentation will be recorded by default. It is the requirement of WACV 2022. And the other little bit of things, so when you are presenting, we're trying to keep the time quite stick to the time so that everybody can have their time to presentation. So I'll show you kind of 5 or 2 if there is 5 minutes or 2 minutes left, and then I think you will have to wrap up your presentations during that time. Yeah. I'm just going to go through a quick snapshot of the program. We'll start with a keynote, and then followed by invited talks, and then we'll have a short break, 5 to 10 minutes. We put it as a 10 minutes, and then 3 papers followed by another keynote, and we'll have a break which is around 30 minutes, and same procedures will follow the second session as well. Keynote 3 and invited talks, short break, papers, and then final keynote followed by a concluding closing remarks. Okay. Just a brief information about keynote speakers. We have from the distinguished professors to entrepreneur, and these talks now linking the workshop topics, and it will be very exciting talks, and we are looking forward to it. Because people are from different geographical locations, we try our best to fit the keynotes timing according to their geographical locations. And similarly, we have also some talks, interesting talks from young early career researchers. Most of them are there in final year PhD. They will talk about some of the interesting work they are doing. Okay. And finally, I would like to thank my co-organizers to help and make this workshop happen during this difficult time. And also, I would like to acknowledge the funding for the projects. We have a UKRI funding, as well as Department of Science and Technology, DST, Government of India, and British Council. And that's all from me. And I'm going to hand over to one of our organizers, Venkatesh Babu. Thank you, and have a good time during this workshop.
Thank you, Ardhendu, for introducing this workshop to the audience. So let me introduce our first speaker, plenary speaker. Our first plenary speaker is Dr. Arjun Jain. Arjun Jain, he did his PhD from Max Planck Institute from Germany in 2013, and he did his postdoc. He did his postdoc from New York University, and worked with Chris Bergler and Jan LeCun. It's a big group in deep learning. Yeah, so he currently works as a adjunct assistant professor at Department of Computational and Data Science at the Indian Institute of Science. Before joining here as adjunct faculty, he was also working as an adjunct assistant professor at IIT Bombay. And he is actually a founder and a chief scientist at UAVIO Labs at Bangalore. And he also co-founded Perspective Code. And before all these things, he also worked as in Yahoo Labs at Bangalore as a software developer, and he also worked in Apple as a researcher. With this brief introduction, let me invite Arjun to give his lecture. Yeah. Thank you.
Thank you, Professor Venkatesh, for that very kind introduction. So without further ado, I'll share my screen. All right. So, yeah, all right. So our topic for today is self-driving at scale. Where are we headed? And of course, to say where are we headed, we have to talk about where are we now. And this is just my perspective of what I see in the industry. And the talk is laid out as follows. So I'll start with some of my work in automotive. I'll give you a very brief history, the DARPA history of autonomous vehicles. We'll talk about two kinds of autonomous vehicles. We'll then talk about where we are headed, this AI first hybrid approach. We'll talk about more when we get there. We'll talk about the data factory. Then, of course, sensors. We'll talk a little bit about sensors and why redundancy is so important and how to incorporate those things. How important simulation is in today's world, specifically for the long tail problems. And of course, finally, how you what are ways to deploy it on hardware. And of course, the $1 million question, when will we get there, right? So just a little bit about my work in automotive. So what we've done is for Mercedes-Benz, we've already launched a product called MBUX. It's already in the car in production. You can buy it, and it basically falls into the user comfort and assist category. At the same time, we are also working with, or I have worked with in the past, Mercedes-Benz, Volkswagen, Apple, Bosch for autonomous cars. Level 3, level 4, and eventually level 5. So I'll talk about both these things briefly and then take it from there. So this is the Paris Auto Show in 2018, right? And this is our group leader, Volker Entenmann, and he's demoing the system that we've developed. So this was an old system, 3-year-old system. What we've done is we've put a camera behind the rear view mirror, right? It's a time of flight camera. And based on that, we realize a few use cases. So we can, for example, detect the 2D joints. And then based on that, we do a lookup for the 3D position of the person's body joints like wrist, elbow, shoulder, etc. inside the cockpit of the car. And based on that, we can realize a few use cases. For example, here you see that because we can distinguish between driver and passenger, when the driver takes his hand, the driver seat is automatically selected. And similarly, even when they take their hand to the touchpad, because we know the position of the hand, the corresponding seat gets highlighted. So the advantage is it's one click lesser. So, it's slightly better UI. There are also other functions such as favorite pose, and lights switch on and switch off. For example, here Volker is showing the favorite pose. For example, if you do the V pose, you can then tie it to various functions. For example, here he has tied it to ambient lighting and so on. You can also tap below the mirror and it switches the lights on and off, right? And a few more of these, say, explicit use cases where you have to explicitly do something. But our aim was always to do implicit, where the user doesn't have to learn the system. Whatever user does, we basically react or respond based on that. So this was then, the next was, sorry. Okay. Yeah. Next slide is, Yeah, so this is then our work in 2020 CES. And here, this is the top line Mercedes Maybach S-Class. And here we have implicit features. Here we also have cameras on the back, and you see how the headrest gets adjusted, to his head size, because we also localize the head position. Here, the door closed automatically. The seat belt presenter presents itself as soon as, you move your hand towards the seat belt based on the state of the car. Again, the sunroof, you can close with this gesture, and so on. There is also the reading light, which I talked about. So you see, you just tap the reading light, and the reading light gets switched on. One very cool feature which exists is, you can choose between the rear view mirrors. Currently, you have to choose left or right and then adjust a rear view mirror. Here, you can just look at your rear view mirror and start adjusting, because we can classify, is it looking towards the left and right, right? Now, we also published a bunch of papers, a few patents during this 3-year tenure at Mercedes-Benz. So I sold my company Perceptive Code from California to Mercedes-Benz, and we had to do this 3-year handover. And this is what we did during that time. Now, the question we should ask is, and we're still talking about interior of the car. The exterior of the car, things are still not in production from our teams. So the question is, why could we only do this in 2018? So to enable the previous application, we needed to estimate the position of hand joints in 3D within the car interior, and people have been trying to do this for a long time. For example, Chris Bregler did human pose estimation in 1998. We did some things in 2010, but the performance was not good enough for industry. And then, as we all know, AlexNet happened. And once AlexNet happened, we were at a place where, it was good enough to be used in industry. So now let's move on to, the autonomous or the automated drive use cases. And I'll just give you a very quick history, 2 slides. So it's not new. People have been trying it forever. For example, the Eureka project, Prometheus, was conducted between 1987 to 1995. And the Vita 2 by Daimler-Benz, which you see here, right? So this is the Vita 2. This could already drive, on the highways automatically for a significant amount of time. Then, as you all know, the DARPA challenge happened in 2004. And the most interesting thing about this competition was that, all participants failed. Because it was a very difficult competition, because to finish this 150-mile off-road track, the main difficulty was, no human intervention was allowed at any level. So none of them could really succeed. The same challenge happened again in 2005. And this time, 5 teams managed to, finish this track without any human intervention at all. And what changed? Well, the biggest change was that Velodyne was starting to supply LiDAR sensors, and all the teams that won, Velodyne was one of their suppliers. So this was something, very interesting that happened in 2005. And then DARPA challenge also happened in 2007, where they did, an urban test environment. So they had an urban scene, and 6 teams managed to also complete the event. Now, this urban scene, of course, did not have the dynamic elements such as other cars, pedestrians, and so on, but they simulated a city environment and not an off-road track. Now, again, talking about autonomous vehicles, we can do this in 2 ways. One is, ego-only systems, where the whole car has to know about the entire environment by itself. So the agent has to know about the entire environment, or connected systems, where a bunch of agents look at the environment, have partial views of the environment, and then share this information with each other. But because we want our system to be robust and not depend on, other agents, we mostly focus on this kind of autonomy, ego-only systems. And then there are 2 ways, or many ways, but 2 main ways to do autonomous vehicles. One is to do autonomy algorithms either using, say, end-to-end systems. And what do I mean by end-to-end systems? End-to-end systems, I mean that, okay, you give the raw sensor inputs, raw sensors, like, the images from the camera, the GPS position, to a giant network, and the network directly outputs the control that should go into the car. For example, amount of steering to turn, should you press the brake or the acceleration, right? So the output is directly driving commands, and this is end to end. I'll talk later about pros and cons of these kind of approaches, but this is probably the simplest one to understand, but it has a lot of difficulty when you actually want to do this in practice. And then there is the modular way. So the modular one is where you break the entire system down into multiple modules, and these modules are perception. So I'll talk about all these in detail. So the various modules are perception, scene representation and localization, prediction of where others will be, or forecasting also it is called, and then planning and decision making. So based on where others are, how should you plan your path around them? And then finally, how to transfer these paths faithfully using control into real life, right? So control also has errors. So you have to also take care of those errors. Now, again, there are a bunch of advantages of doing these kind of things, but also disadvantages. And we'll try to compare these in the next slides. Now, but before we get to that, I would like to discuss this stack, right? So end to end, there was not much to discuss. You have a giant network. In comes the sensor and outputs, and out goes, the vehicle commands. Now, modular systems, let's look at it in a bit more detail. And let's start with the first one, perception. And perception is what I do most. I'm a computer vision person. And so we'll talk a little bit more about perception and less about others in the interest of time. So perception essentially means the ability to see, hear, or become aware of something through the senses. Now, the only senses that an autonomous agent has are, the various sensors that we have deployed on that agent, be it vision, radar, LiDAR, sound, whatever, right? Now, perception is a very difficult problem because of the tail, the long tail, and we'll talk about it. So let's just look at this image, right? So any image such as this one, suppose our car is driving and the car gets to see this. Now, what all will the car need to do? So the car will need to understand, localize, and classify these moving objects, right? Such as these cars and cranes. It has to identify these static objects, such as the traffic cones. It has to identify these road signs on the side of the road. It has to identify these overhead road signs. It has to identify the traffic lights and its state, right? That currently it is red and we should not move. It has to identify the lane markings, various kinds of lane markings, solid, dotted, yellow, double yellow, and so on. It has to identify and read these road markings. So it says halt. It can say school ahead. It has to identify curbs, because curbs are special, because the most important objects, pedestrians, humans, are usually found on these curbs. We have to identify crosswalks. And we also need to know if we are in a residential area, are we in a tunnel, are we approaching a toll booth, etc. So a lot of things a perception system needs to do, right, for self-driving. Now let's look at just one of these use cases, right? So let's just look at moving objects. Yeah, so let's just look at moving objects such as these. So now moving objects can be of so many different kinds, right? So there can be a moving object which has met with a collision, right? And it's not moving anymore, such as this one. Now it could be a pedestrian, it could be a biker, it could be the back of a truck, it could be a bigger truck. You also need to, solve for subtasks such as the state of, say, the blinkers, the state of brakes, right? Is it parked? Has it met a collision? You also, things like people walking with prams, people cycling, special vehicles such as fire vehicles, emergency vehicles, again, another police vehicle, which is an emergency vehicle, a crane, and so on. And now let's look at, again, a subtask of this, right? So let's now look at only, say, moving vehicles, right? And then these moving vehicles can also be of so many different kinds. Now, another problem is that, 97% accuracy is not good enough. And finally, the system after sensor fusion and everything should get to, 99.9999% accuracy, which is one failure in a million tries. Otherwise, again, the system is not safe enough to be deployed in the world. Now, let's talk about the long tail problem. So why is it difficult? I mean, moving objects can be of so many different kinds. So there are all these specific things. And one easy example is, suppose we want to capture, say, aggressive or, conservative driving behaviors by humans. So by definition, these are not there, right, in training data because they are the tail end. So we need to so we get data for this part of the distribution, for the part around the mean, but the tail end is where the system fails and we have very little data for this part of the distribution. Yeah, so it's all about, so in autonomous driving, it's all about the long tail. How do we fix the long tail? Yeah, how do we get specific data only for the tail, or what can you do when you're in the tail? So this part is essentially solved by almost everyone, right? This is an example of traffic sign recognition. And at the outset, you might feel, okay, traffic sign, very easy problem, planner object, right? But let me tell you a little bit of, so we have done this for Bosch and this is already in production, but it's again a driver assist feature. So it's not something which is safety critical yet. Why? Because we need high accuracy. Again, it cannot fail. It should work without HD maps. We don't have a very high definition view of the city. The biggest problem is, data imbalance. So we have 600 classes, and for some classes, there are as little as, say, 5 examples. So how do you deal with that? And it may be a very important class, which we really want to solve. And finally, in the end, you want a low latency, high accuracy system. And what we came up with was a complicated architecture such as this one, where we first run a detector which finds, the traffic sign. But again, we cannot have 600 classes in this detector. So we simply have a bounding box and a shape class, example, say circular, rectangle, and so on. Then there is a cascade. So after when we get this, it then goes into scaling. We read text on it, but at the same time, we also put it into a classifier. And then the classifier classifies this top level sign into then a fine grained sign. And then there is also parent association, because traffic signs can be nested, there can be many together, and to make sense of the traffic sign, you actually need to understand that nesting. So something as trivial as a traffic sign is already, a complicated system in hardware. Now, once we've done perception, right, high quality perception, we then need to represent this in the 3D scene. So we need to then lift it to 3D, either with the help of sensors or by making sense of, by using sensor fusion, by doing structure from motion or other vision techniques. So here is one scene representation. So in scene representation, what do we need to do? We need to localize ourselves. And with respect to us, we need to know where the other objects are. So here it has, base. So you see it has localized that here is us. And then here we have a pedestrian. So here corresponds the pedestrian. Here we have a traffic light, the state of the traffic light, right? This is the line, the halt line, which the car should not exceed. Here are other vehicles, other objects of interest, and so on. So after perception, we do scene representation and localization. So scene representation and localization. And how is localization done, especially if you have HD maps? So suppose the most accurate way to do localization is to have a very high quality 3D map of the city or of the area. And then when we collect 3D information of the scene at that point. And based on that, we map very accurately where we are. So we do some kind of a high-speed ICP, iterative closest point algorithm, to match our observation of the point cloud to the view of the city that we have. And based on that, we can localize where we are in this city or in this layout that we have. Right. So this is then localization using LiDAR. You can also do it with just vision sensors without HD maps. A lot of people are trying to do that. Tesla is one of them, right? So they've even removed radar from their latest stack, and they're now going for the vision only solution. Now, after doing your perception, scene localization, and scene representation and localization, yeah, so localization, again, you can do it using LiDAR, or you can try and do it only using vision input. So here we have 8 cameras from Tesla, and Tesla is doing your localization just based on these image inputs.
The bicycle will go straight through the red light.
Yes, sorry about
And
that.
it could also believe that the bicycle will go through the light.
I'll just mute this one. Sorry about that. Yeah. So now, once we have represented the scene, so once we have a 3D view of the world, and when we know where we are and where the other objects of interest are in this 3D scene, we then need to also predict where others will be. Now, why is this important? Because we have very little time to react for a car, right? Suppose it was drones and we don't, so we assume that there are no other, so for drones, it's not that important to predict where others will be, because we usually have a clear path. But say for this car, we really need to know, sorry, let me play this video again. We really need to know where this bicyclist would go. Will it go straight, right? Will it turn right? Or will it just stop right here? And you see that we somehow predict this. We forecast where the bicycle will be, say 1 second later, and here the prediction comes out that it'll stop at the traffic sign. So this is important, because only based on this prediction we will then plan what to do. Yeah. So after we have done our localization, we then need to predict where others will be. And then once we know where others will be, for example, we have already predicted that there's a, this thing, then we need to plan what path we should take. So here it's kind of a search problem, and then we have so many paths, and then based on that we have to choose a path which is of minimum cost. You define the cost based on, say, which takes you from your source to destination in the quickest time, doesn't meet any accidents, is smooth, jerk free, and so on. So then you have to choose the path. And finally, once you have the path, you need to faithfully transfer it into control. You need to decide how should you actually give the various actuations, such as, how much gas should you press, how much of your steering should you move, so that it can faithfully, transfer that path onto the road. I'll not talk about details of control and the sources of error, but again, this is not completely error-free, and you have to also account for errors. All these stages have errors, and one thing probably you already see, which I'll talk about later, is the cascading effect of errors and early errors. Yeah. So control. So we talked about perception. Based on perception, we do scene representation and localization. After that, we do forecasting or prediction of where others will be. Based on that, we do motion planning, how our motion should be, and then finally transfer it into control. Now let's compare the two things that we have seen, modular versus end-to-end, right? So modular, what are the biggest advantages? So for the biggest advantages from big scaling industry point of view is that it helps us to divide tasks within the team, and engineering is easier and more interpretable. Also, we can test each module in isolation. So we can have test cases, and each module can have, a quality assurance. Also, it is easier to hand code rules or priors for each module, because each module is separate. Maybe we can put, you can see that putting rules and priors into each of these modules is easier than if we had a giant neural network here. So, but then what are the cons? Where do we lose out? So each step of the process is performed in sequential modular silos, meaning none of them know about each other, right? Each of them are developed in silos independently. Also, the stack has to be manually tuned for whenever we introduce any change. So because this is all, independent, whenever we introduce any new change at the end, we need to then manually tweak each of these modules. Also, limited information is shared across these modules, right? So we have the cascading effect of errors, which we just talked about. So these earlier errors can hardly be compensated by later modules. This is one of the biggest problems, in my opinion. And we have to rely on modules for each problem. For example, we have a stop sign classifier, right? We can detect and classify stop signs, but then suppose it's not working due to some tail end problem. For example, foliage, meaning there are leaves in front of the stop sign. So this is a real life problem by Tesla. And then if you want to solve this, then you have to introduce additional modules, which is again very, very difficult to scale and highly expensive and slow. Now, if we talk about this end-to-end, so if we contrast it with end-to-end and look at, the pros of an end-to-end system. So an end-to-end is where, like I said, you give all the inputs to a giant network and the network just outputs the various control outputs. Now, of course, the biggest advantage is, it's a single AI system. So it's very simple and it's trained for the end task. Previously, we could not really train all modules for the end task. Here, we can really train this neural network for the end task. But then the problems are that it's difficult to add priors and rules. And the lack of interpretability for validation and safety is again very painful. So it's not clear how to solve this. The people who are trying, I'll show you later, but they have the same problems. And because it's this one giant model that you want to train, it really needs a lot of data, right? Because you cannot train it in parts. So it really needs to know about the entire system. It needs to see almost all kinds of combinations of the various actors in our environment. So this is Wave, a startup from a very well-funded startup from Cambridge, England, by Alex Kandal et al. Earlier, he was doing great work in uncertainty, and great people have joined his team. So this is, his car learning from few examples. So they seem to have solved the example problem a little bit, but again, this is just a single video. So here you see a small Renault car, and just with a few examples, it just learns to drive on its own for certain use cases. Yeah. So this is end to end. Now, this is, I guess, this is, in my view, where we are headed, right? So we should not be doing either this or that, and we should try and find some middle ground. And one way to do this is the kind of work that Aurora, the trucking company, or Professor Raquel Ultrason from WACV is doing. And what they are saying is, at least merge these two aspects, merge the perception and prediction, or perception and forecasting. And the kind of things they do, I'll show you later, is where they say that, okay, let's not just give bounding box outputs for the various actors in the environment, like cars and trucks and signs and humans. Instead, let us directly give an occupancy grid, meaning let's just know. So after forecasting, let's just know what is a good place for the car to be and what is not a good place for the car to be, right? And let's just try and do that. So what are the pros and cons? Well, they're kind of obvious. The modular approach helps us to divide tasks within a team. Engineering is easier and more interpretable, and hard-coded rules are easier to include. And of course, the downsides still remain for this kind of a hybrid approach. So like I was saying, what this is very new work, and all these papers will mostly be from her group. And these are all, CVPR 2021. And you see here that what they are now doing is, they're taking the sensor input, be it LiDAR, radar, vision, whatever. And then I'm not going to details of how they're actually doing it, but they are essentially giving you the occupancy. So after forecasting, they're giving you the occupancy. And based on this occupancy, you can then do the motion planning. So there are ways to also do this using a learning-based approach and so on, but that's not the topic for today. And that's not also very important in my opinion, but in my opinion, this is a game changer. This is what everybody should be doing. And this is also what we are kind of gravitating towards in industry. So with some of our clients. Right. So this is basically what the main message for the talk was. And now I'll talk to you about some of the sidelines, right? So things that are needed and are very important to get to at scale, because that is one of the topics for our talk. So how to do things at scale. Now, to do things at scale, earlier it was easy, right? So earlier pre-deep learning era, we had simple tools and everybody had access to these simple tools, and we could all kind of use these tools to kind of build whatever we wanted to. But today, if you really want to do things at scale, specifically at autonomous driving scale, we need to first build a factory, right? We need to build this data factory, which we call it, or the data loop, or the data engine, like Tesla calls it. And once we have built this factory, then we can build a lot of, cars or anything from, so you can then pipe a lot of things through that factory in that assembly line. And what is that factory? Well, for us, the factory kind of seems like this, right? So you start with some initial data. Remember, we're doing things at scale, so you cannot really solve for the end problem directly. So you start with some initial data. You then deploy it, you train a model. You then deploy that model directly onto the car. So to do this, you need to have capability to do, over the air update. So over the air update of the model is very important. And this is one core aspect which you should think about if you really want to do things at this kind of a scale. Then once you have deployed it on the car, you have to come up with, say, triggers to identify inaccuracies. This can be done in many ways. Some very simple, such that, suppose you want to find traffic signs, maybe just find all the frames where the car came to an absolute halt or the car started from a halt, right? And then probably some of them will have traffic signs because the car stopped and started from there. So you collect, and then there can be more sophisticated ways of finding errors. So this is a complete field in itself, uncertainty, online learning, and so on. But whatever your method is, you need to make sure that you have enough bandwidth. So now there is an engineering issue that you need to then send it back to your, so you need to collect these samples, right? So suppose we were making errors inside a tunnel. So we collected a lot of these tunnel samples, and then we need to send it to our data set, right? So to augment our data set. But you need to kind of take care of the fact that we only have so much bandwidth. Every car can only transmit so many images per day, because it cannot transmit all image data that it collects. It collects, terabytes of data per day, and it can only transfer maybe a few gigabytes, maybe like single number gigabytes of data, that too where we have very good networks, right? So this is what we need to really build to even start working. So what people are doing, one of our customers, what they are doing is, and Tesla did this as well, that they retrofit cars already with cameras, which do not have the final model deployed. So they have one model deployed, and then there is a shadow mode, right? So the shadow mode model is deployed, and then you just collect data based on the thing. And then as soon as you think your model is good enough, you just enable the other system to start, and then your car suddenly becomes level 3 or level 4. So just for guys who do not know the difference, level 3 is just driver assist. So it should sound an alarm where it is not able to basically drive the car anymore. And then there is level 4, where the driver, the car is completely autonomous. You don't need a steering wheel for a particular layout, for a particular part of the map. Level 5 is where you can drive everywhere, right? So in my view, we'll only get to, level 4, and then bigger and bigger level 4, and then level 5 is maybe a few years down the line. Now, sensors, of course, sensors are very important, and we use, all different companies use different kinds of sensors. There's a lot of work and advancement happening in the sensor space, and we should not discount the role of sensors. Good sensors can, solve half the problem. But again, sensors are expensive. So this is chicken and egg problem. Now, sensors should be complementary and redundant. For example, this is, I think this is one of the autonomous car companies, and they have these redundancies between vision, radar, and LiDAR. And we should always remember, the big problem that Boeing 737 MAX faced, which was it did not have proper redundancy for the angle of attack sensor. And because of that, it lost billions of dollars, right? And so many unfortunate accidents happened. So it only had a single point redundancy. So there were only two sensors, but there was not a breaker sensor to kind of realize which sensor is giving the wrong and which sensor is giving you the right output. Now here we compared some sensor stacks, and you see that Tesla has the minimum amount of sensors because they also had to be, cost efficient. And these two are more from a research point of view where they really want to go completely autonomous. And Google Koala, one major feature is, their near field LiDAR. So they have a lot of near field LiDAR, Google proprietary LiDARs, which are really amazing and gives them a very, very nice perception. Again, the same thing which I mentioned. So Tesla, not so, not so great specifically, for not manageable. So most corner cases are not manageable or with serious restrictions. Google Koala is really good, especially for the near field. And they use two different kinds of LiDARs, and Uber XC90, though it's not doing much work now, has missing corner LiDARs at the front. So this is again a problem. Now, to really do autonomous driving, simulation is really, really important, right? So all kinds of simulation. And so this is just one simulator. A lot of these companies are investing on their own simulators. So this is Waymo. Waymo has, so this is already old, and I'm sure they've done a lot more by now. So Waymo did already, so they have 25,000 cars in simulation. They are doing 10,000 miles per day, and they have, 7 billion miles simulated. And this is already old, and the figures would have increased by now. But this is still, in my opinion, not. So the next age of simulation is the kind of work which was presented by, again, Professor Raquel, again in 2021 CVPR. And I'll show you some of her work. So this is basically, learning to generate realistic traffic scenes from real footage or otherwise. Here we have, generating safety critical scenarios, because this is most important, like how to create where a car comes in front of a car and all those difficult cases which happens in real life. But when you actually collect data, or when you actually create rules for a simulator, these kind of cases get missed out, and thus they do not get tested and validated. So this is one example where they take a step further. And again, this is, I think, where we are headed, where they actually simulate all the way to sensor. So this was a CVPR oral paper by them, GeoSim. And you see what they have done is, sorry about that. What they've done is, they're doing photorealistic image simulation with geometric aware composition. So they want to simulate this kind of a traffic situation, and they do it in a geometrically consistent way in 3D. And they have a way of coming up with, 3D models of cars in a very cheap way, and then they can paste it onto various places. They compare their work with, graphics-based rendering and then compositing, but this is not, the graphics way is not scalable. So the CAD computer-aided design way is not scalable, because you have to give it proper materials, proper colors, various, and this doesn't look as good as their approach, of course. So this is where we're really headed, simulating not just our traffic and realistic scenarios, but all the way to sensors, then having a closed loop, right? You make, where you're making errors, you simulate those kind of situations, and then you train with them, and then you again test with newer simulations where we think we might fail. And once, this closed loop simulation finishes, and you see there is not much human intervention in this pathway. So this is something that can scale. You also need test facilities. No matter how much simulation you do, eventually you need to put it on a real world car and then test it in the real world. And before you put it in the cities, you would probably want to test it in a safer environment, such as this test facility that Google or Waymo now has, which is in Castle, California. This one is 91 acres. Most of the bigger companies have such facilities, and they need to. Hardware is something that we should not discount. I mean, you can kind of think about, like, how much compute this really needs, how many models that really will be deployed finally on hardware. And so companies like Tesla have, realized that they should really invest also in their own chips. So they're doing their full self-driving chip, which can, do they claim 144 tera ops, right? So you convert your model into 8-bit unsigned integers, and then you can have 144 trillion such operations per second. NVIDIA is coming up with the Drive PX Pegasus, which is supposed to do 320 teraops. So, and it will also have this ASIL D automotive certification and functional safety. So hardware is again very important and very critical, and this is again where people face a lot of problems to production, and not just deployment hardware, but also training hardware. So Tesla supercomputer, the Tesla training servers, this is one of the biggest supercomputers in the world. So I think they were ranked number 5 at some point, right? So you really need to have so much training capacity to be able to train all these models. And if you think about all the details, training becomes very tricky because it's a stack, especially in the modular architecture. Now different teams are working on the same backbone. If one needs to change the traffic sign, but it comes from the same backbone, then how do they change their traffic sign without affecting, say, the vehicle recognition and detection? Do they change the backbone? When do they change the backbone, right? Or do they just change their head? So it's complicated, especially working in large teams, but there are ways to make it work. Also versioning, all that becomes really important. So these are a bunch of companies which are now doing autonomous driving. The last 4 are the newer ones. Android is doing something special where they have probably the best teleoperation. So they're doing autonomous driving for the highway using trucks, and then they have teleoperation. So whenever the autonomous system is not able to perform, it does a very graceful handover to a human pilot. So just like these Predator and the Hornet drones that are flying, you will also have operators driving these autonomous trucks, and they seem to have cracked it in a nice way. So they are based out of Stockholm, Sweden, and now they are selling their trucks to a lot of companies. Wabi is by Raquel. Wave is something we talked about. Cambridge. Aurora is the trucking company. Okay, we have 5 more minutes. I will quickly wind up and open the floor for some questions if you have. I've been very lucky in my journey to have worked with a few of these companies for this autonomous driving dream. Of course, there is a lot of business that will come up when this autonomous driving really happens. And of course, the $1 million question is when. And I will take, Professor Olson's. So I think this was one of the very good answers, which I liked. And what he says is, he just linearly interpolates. So on our y-axis, we have miles per disengagement. Like how many miles can a system drive before the driver has to take over? And here 10 to the power 8 is kind of an average for human drivers. So after 10 to the power 8 miles, on an average, humans meet with an accident. Yeah, so 100 million miles. And here on the x-axis, we have our date, of course. So we are currently, say, in 2022, somewhere here, right? And maybe we are able to do around 10 to the power 4 miles. And where we have to get to, so this is level 5, right? Where a car will be able to drive everywhere. And if you just extrapolate, it maybe comes to somewhere around, I don't know, 2037. Yeah, but I hope, and I'm sure that we will get level 4 much sooner, where we are able to drive in constricted environments, be it campus environments, be it, certain roads, certain cities, certain areas much sooner. And let's hope, we get it already this year. I mean, I know people have been promising this forever, this year, next 5 years. So yeah, I'm hoping we will get it somewhere around here, at least level 4 in some cities. We already have it, but more mainstream. And this is a reality which we will soon see. And now I will leave you with just a video from Tesla full-scale urban autopilot. And this is my last slide. So thank you very much. And now I'm open for any questions you might have.
Thank you very much. That's a very, very fascinating talks, and some of the things even now we do read research papers. Even we didn't know that quite a lot of things are ongoing at the moment in different company, different research directions. So yeah, I have one question, sir, from Aditya. For virtual scene representation, what objects in road network scene do you think are most important as far as testing of sensors is concerned?
Right. So we want to be able to detect everything that you need to know before you can drive, right? So as a human, what objects do we notice? So we notice you need to know about traffic signs, you need to know about objects. So everything that I discussed in that slide, right? So moving objects, static objects, traffic signs, curbs, sidewalks, the kind of locality we are in, and so on. I hope that answers it.
Okay, thank you very much. While people are typing, so I have a couple of questions about, one you talked about this simulations of a real world scenario into a CAD space. So how much work has been done? For example, if I'm driving in Indian traffic conditions, can I translate the real world scenario to a CAD or virtual scenario so that I can try to test the performance of various sensors?
That's a very good question, Professor Bera. So people have done, so there are two ways to do it. One is where you have some measurement of this real world, say using video or any other sensors, and then you try to kind of transfer that into your virtual world, right? So this is limiting in some sense. There are papers, like I mentioned, also in CVPR 2021, which do this to some extent. Also, there are ways to kind of generate that in a rule-based scenario, and then there are ways to kind of merge these two things. But to the best of my knowledge, we have not really tried it for the Indian condition as much. Professor Jawar, who will give the next keynote, may shed some more light on that. But to my, to the best of my knowledge, not much work has been done specifically for the Indian condition. And the Indian condition is very special because I think it is about where you really need to only do, local predictions, where you don't really need to know about a lot of other global signals, and you just need to know how far the next car is, and you just go that much. I mean, so very interesting work in this unstructured environments, which Professor Jawar is going to talk about.
Okay, thank you. There's another question from Professor Liu. Is that really possible to predict the intention of other road users for motion planning? What accuracy can it?
Again, great question. Of course, there will always be errors, and a human can, come all the way to a sidewalk and just stop, and then it's almost very difficult. But there are certain cues, for example, gaze, if he looks at the car and so on, which can give us some hint. And remember, here we need to predict. So on the highway, maybe we are able to really predict where other cars will be based on the signals that they give us, the current speed, their indicators, their brake lights, and so on. Because on the highway, specifically in countries like the Western world, they will really follow that. Like if they do a hard brake, even in real life, even with a human, they will meet with an accident, because the human is doing the same. The human is also extrapolating and predicting, forecasting where they will be. So yes, for those kind of scenarios, we can accurately forecast where they will be. And for the short forecasting, like 1 second forecast.
Okay, thank you. This is my final questions. You mentioned about in an ideal scenario, we'll have 99.9991 in one fault in a million. So at the moment, the video you are showing, the Tesla, and there are some works other companies have done. So what kind of accuracy they are getting it?
Yeah, so good question. So my customers, we are not getting 99.9999 for sure. And remember, this is not just for perception, but for the final system, right? The system behavior, we should be able to do 1 in a million. Tesla Autopilot, wherever it works, it is doing, and the hope is that because they have now almost 600, 800,000 cars on the road, they are able to get all these engagements, right? So whenever a driver does any engagement, they get this kind of the tail end. So yeah, we're not there yet, but hopefully by solving the tail end, the long tail problem, we will get there. So we definitely are not there, specifically, the kind of customers we are working with.
Okay. Thank you very much, and it was a pleasure to have you in this keynote. And thanks a lot. Yeah.
Likewise, Professor Bera, it was a pleasure. Thank you so much for having me.
Okay. Now we'll have next two talks as a invited talk, and I think the first one we'll have from Jogendra Kundu, and if Jogendra, you can start your sharing, and while Jogendra is preparing his presentation, I'm just going to give you a quick info about him. And Jogendra is a research intern at Facebook Reality Labs, as well as a Google PhD fellow and pursuing a PhD in at Indian Institute of Science, Bangalore. Okay, and he has received outstanding reviewers awards at NIPS as well as CBPR, and published more than 10 papers in top tier computer vision conferences such as CBPR, ICCV, ECCV, and NIPS and AAAI. And he's going to talk about the generalized and adopt source-free domain adaptive semantic segmentation. I'm going to hand over to you, Jogendra.
Yeah. So, am I audible?
Yeah.
Okay. Yeah. Hello, everyone. I'm really excited to walk you through our recent research work, which is titled as Generalize and Adapt. So this was published in ICCV 2021. And this is a joint work in collaboration with Google Research. So I'll first introduce the problem setup and what are the different settings that we focus on. So the general unsupervised domain adaptation problem involves a labeled source domain dataset and an unlabeled target data. And these are drawn from different data distributions. So the goal is to effectively utilize samples from both the domains to train a model that performs well on the unlabeled target. So conventional domain adaptation techniques assume simultaneous access to both domains, and this enables them to characterize the domain gap and propose techniques to align feature representations for both the domains. Just a second, yeah. So recently source-free domain adaptation is introduced to relax the concurrent access assumption in a vendor client setting. So what is a vendor client setting? So consider a vendor organization that has access to large scale level data set, and this can be used to train a supervised source model as shown below. On the other hand, the client organization wishes to deploy it in a target environment and has access to unlabeled target dataset DT from the deployed environment. And here the client has to prepare the target specific model for the better deployment performance. So most importantly, the vendor and the client organization cannot share their data due to privacy or proprietary concerns. However, the vendor can trade the source train model with the client. Now the client's task is to perform source-free domain adaptation to obtain the required target specific model. Now we'll discuss the key insights that we'll explore in this work. So to tackle this practical domain adaptation setting, we propose generalize then adapt, where the vendor and the client adopt specialized tailored sort of learning techniques for the final target adaptation. So here the vendor aims for domain generalization to produce generic source model in order to serve a wide range of unknown targets from several future clients. So now the task for each client is to utilize the given source model to obtain an effective target specific model. Natural question that arises is how can we enable the vendor to serve a wide range of unknown clients while having access to only a single source domain in the beginning. So to this end, we draw motivation from the multi-source domain adaptation MSDA or domain generalization techniques in the literature. So the idea is to leverage multiple source domains to enhance generalization to unseen target domain in future. Thus, we cast the vendor side training as a multi-source learning problem. So in order to clearly present our key insights, we first illustrate the concept of hypothesis support. So considering access to multiple source domains, we train a multi-head source model. For any target TJ, the expected target error for the first head can be expressed as the expected loss over samples from the target dataset. So here H is a hypothesis or a classifier which belongs to hypothesis subspace H1, where H1 is a subset of the larger hypothesis space A as shown in the figure. Similarly, for the second head, the target error is shown as in the equation. And here the H belongs to the hypothesis space H2, and which is a subset of the largest hypothesis space, that is A. So the same can be done for any head of the source model. And in an ideal scenario with simultaneous access to all the data, the ideal target hypothesis HTJ would yield the minimum target error that can be obtained as shown in the equation. However, in a source-free setting, if you H2 presents the best support for the target TJ, as it is the closest to the given target hypothesis HTJ. So you can see in the figure, HTJ becomes the closest to the hypothesis H2. So intuitively, like the domain, a particular source domain could be the closest to the unknown target domain that you are encountering in future. So to summarize here, the hypothesis support is a hypothesis subspace or a union of subspaces that indicates availability of support exhibited by the shared source model. So now we explore potential hypothesis support configurations. In other words, what are different ways to utilize multiple sources from a hypothesis configurations? So first we consider the traditional empirical risk minimization approach, which is denoted as ERM. So here a single output head is obtained on samples from all the domains with equal weightage. So the second configuration is denoted as domain experts or DE. So here each model head is trained on a specific domain. Thus the number of output heads is equal to the number of available source domains. The third configuration is denoted as leave one out or LO. Here the leave one out head specific to a particular domain is obtained by training on samples from all domains except that particular one. So similarly, similar to D, here the number of output heads is equal to the number of source domains. And next we introduce some additional configurations, that is DE++ and LO++. So here DE++ configuration includes all the domain experts heads alongside the ERM head, and thus making the total number of heads as the number of domains plus 1. And the same is followed to extend LO to LO++. So by doing so, we are able to strike a balance between the domain generic and domain specific supports, because ERM is something related to domain generic support, and DE and LO are more towards domain specific supports. So next we show a pictorial representation to analytically assess the suitability of candidate configurations. So here we'll be comparing the configurations ERM, DE++ and LO++ as depicted in the table. So in this particular example, we are showing the target TJ1. We observe that one of the LO++ head is closest to the unknown target, indicated by the dotted green line. So thus LO++ configuration would provide a better support for this particular target. We saw that more examples assess that. So if you look into more examples, one can assess that none of the configurations would win every time. So as you can see, tick marks are shown for different cases to different configurations, like ERM is winning only once, D++ has winning only once, and LO++ is winning most of the times. So under limited heads, LO++ covers the maximum support area, thus is most suitable for the vendor side training. So with this, we move into the implementation of the vendor side training. So the next important question is, how can the vendor obtain multi-source data? So this is a crucial because the annotation of multiple domains is expensive and time consuming, specifically for dense vision tasks such as semantic segmentation. So thus we, as a way around, we propose to use diverse level preserving augmentations to simulate multiple source domains from the available single level source domain. So here we give an insight into how new domains are simulated through augmentations. So we consider a hypothetical data generation process where a source sample excess comes from a data generator function phi. The input to the phi function are the causal class level factor Fi and the non-causal, non-causal domain related factor for the simulated novel domain. So next we apply domain varying class preserving augmentation T as shown in the equation. So see, since T is a class preserving, there is no change to the class related factor Fy. The original domain related factor Fs is replaced by Ft plus gamma Fs. Here Ft is a augmentation related domain factor, and the original domain factor Fs is weighted by the factor represented by gamma. So in other words, the augmentation T modifies the non-causal domain related factors to simulate new domains. A natural question that arises is how to choose the most suitable augmentations for domain simulation. So towards this, we hypothesize that a suitable augmentation should effectively suppress the original domain factors Fs. And based on our formulation, the criteria would be that mod gamma is less than 1. So which indicates that the suppression of the original domain factor Fs. So since the data generation process is hypothetical, we need to come up with a surrogate criteria to actually realize this in practice. So to this end, we use standard source pretrained model HS. So HS can be found by empirically minimizing the standard cross entropy loss on the original source dataset. So using HS, the practical selection criteria is shown in the equation. And here the first term in the empirical loss performs HS on the augmented source data. And the second term is the same on the original source data. So we apply a threshold tau on this difference as shown in this equation. So as HS is biased towards the original source domain, this criteria indirectly measures the residual original source domain information gamma as shown in the top. So in other words, this source bias, the dependence is reflected in the performance of HS, and this can be leveraged to measure the original source dependence in the augmented samples. So look into like how this is used in practice, essentially. So next we apply this criteria on the set of candidate augmentations, which will be depicted on the x-axis. So first we show the performance on the standard single source pretrained model on the original source data as the dotted blue line. Now compared to this, we observe that performance does not drop significantly for weaker augmentations such as blurring, rotation, noise, etc. Hence, there has higher source dependence and are unsuitable for simulating new domains. Whereas strong stylization based augmentations such as FDA style, style log or ADIN, and we also use some of the other augmentations like snow, frost, and cartoon, and we observe a significant drop in performance, which indicates their low score dependence. So thus they are more suitable to simulate novel source domains. So with this, we move into implementation of the network architecture. So now we describe the vendor side approach in the training paradigm. So based on our analytical insights and the device, so yeah, based on the insights that I discussed now, we devise this architecture SOMAN, which stands for Source Only Multi-Augmentation Network. So SOMAN is a multi-head framework implemented based on the LO++ configuration that we discussed. So here the global head HG is trained according to the traditional ERM technique, that is using data from all the domains. And the kth leave one out head is trained using the data from all the domains except the kth domain. And all the classifier heads are trained simultaneously in a supervised manner with a standard cross entropy loss. We recognize that our proposed SOMAN framework may lack the ability to capture inductive bias. So that is, it may not learn the scene level prior knowledge specifically useful in dense prediction tasks such as semantic segmentation. So the use of existing per pixel prediction leads to certain issues. So the issues are merged region or splitted region kind of problems in the predictions. So to combat these special irregularities in the dense prediction tasks, we propose CPAE, that is the conditional prior enforcing autoencoder. So it is conditioned with the domain generic representations from the ERM classifier head. And to inculcate the modeling of the plausible scene augmentations, the CPA is trained to align its output distribution with the source level distribution. So next we describe the client-side training approach, where the source-free adaptation is performed. So as the vendor shares the source trained model SOMAN, every client has to have the ability to choose the optimal classifier head that best caters to the specific target domain. So we propose to use the classifier head HK prime that exhibits the lowest average self-entropy loss on the given target dataset. So this is because a low cross entropy loss corresponds to the high confidence. So we can say that the source domain K prime is the closest to the given target deployment scenario. So using the optimal head K prime and the CPI, we extract reliable pseudo levels for the target dataset using a simple yet effective confidence thresholding technique. Next, we use the extracted pseudo levels to perform self-training. So, but we update only the last layer of the backbone, as this preserves the task-specific knowledge of the optimal head K prime, which has learned during the vendor-side supervised training. Next, we illustrate the key quantitative results of our work with comparisons to existing state-of-the-art techniques. So first, we evaluate the vendor-side training approach on domain generalization task and also on domain adaptation from GTA to cityscapes. We observe improved performance as compared to the state-of-the-art. And next, we evaluate the overall framework on standard GTA5 to cityscape benchmark for unsupervised domain adaptation. So we compare our source-free approach against both source-free as well as non-source-free prior art techniques. And despite the challenging source-free restriction, we are able to outperform even the available non-source-free prior works, which actually assume access to both source and target data simultaneously during adaptation. We also evaluate our approach on the online and domain adaptation from real-world NTHU cross-city dataset. So here the prior arts operate on the conventional setting of adapting from leveled cityscapes to unleveled NTHU. Instead, we first perform source-free adaptation from the leveled GTA5 to the unleveled cityscapes. So this is followed by online adaptation to the unleveled NTHU dataset, where the cityscapes is inaccessible under the source-free constraint. So we compare against these prior arts, and we are able to outperform them even without accessing the intermediate cityscapes levels. Next, we illustrate the quantitative results of our approach. So we observe that the vendor-side model generalizes better than the baseline single source model. Further, the CPA-based structural regularization is able to improve the performance even further. So this enables the client-side model to resolve the merged region and splitted region problems that we discussed before. So to summarize, we focus on source-free domain adaptation for semantic segmentation in a vendor-client paradigm. The vendor organization has access to large-scale labeled source dataset, while the client has access to unlabeled target dataset. However, data sharing between the vendor and the client is restricted due to proprietary and privacy concerns. The vendor may still train a supervised source model, and they are allowed to share this model with the client. Under the practical setting, we propose a generalized strategy to enable the vendor to serve a wide range of unknown future clients. This is followed by sharing the source trained model. We also propose an adaptation strategy for the client-side training, and this is able to provide better performance when we compare even against the available non-source prior arts. Yeah, so with this, I like to conclude. So please refer to our paper and project site for more details. I think we can take more questions now. Thank you.
Thank you very much. It's a nice presentations. Any questions from participants? Okay, just one question from me. What I'm thinking, you talked about this the gap between the source and the target. I'm proposing an example. For example, I asked something to Professor Jain about a driving scenario in a Western country, yeah, and then a driving scenario in an Indian traffic situation as a domain, as a target domain. So how do you think such kind of model is going to adapt into from the source to target domain?
Yeah, so it turns like it actually depends on like how much domain gap we're talking about, right?
Yeah.
So like there are some works on like models trained on like US based cities and they apply it on like Europe based cities, and that is considered huge domain adaptation problem, because we see like different kind of buildings and different kind of structure in Europe, right? And then comparing with India, it will be like a even more domain adaptation, right? Because like a lot of things actually change, and the appearance of a lot of different objects vary, like it changes a lot when we come to the Indian context.
Okay.
So yeah, that is going to be like even like one of the most difficult problems in that way, like and from the domain adaptation perspective.
Okay.
So,
Okay.
like in domain adaptation, we usually consider like in the target data, we don't really have any levels. But in this kind of like huge domain gap kind of scenarios, we do have to consider like a semi-supervised kind of work instead of a fully unsupervised
Okay.
kind of scenario. Yeah.
Yeah. Okay. Follow up the another question to your suggestions. Do you think if we have a kind of a multimodal or multi-source data from a given source data, in the sense, for example, for a given traffic scene, you can have a multi-view of the same scene. Yeah. Do you think that that kind of information or any other multimodal data, for example, LiDAR or other depth information, could also enhance the performance in such kind of a domain adaptation?
Yeah, I think definitely that could help, because like in domain adaptation, like the domain gap is like what is the distribution gap? Like, so if X is the input, what is P of XS and what is the P of XT, right? Now, if we consider X is a multimodal data, so we have like more information in X. So essentially that gap will also reduce, right? Because there could be a different domain where the gap is less. Maybe visual domain, the gap is huge. So it can like extract those informations. And
yeah, okay, thank you. Yeah, there's one more question from Professor Liu. What are the underlying foundation for such learning, and why is it feasible?
So underlying foundations will look into like, so there are like available some theories on like the convergence of domain adaptation problems. So because it's like unsupervised domain adaptation problem, so we have to look into like, okay, if we have access to a unlabeled target, what best we can do with the given source. So you try to do some extra things in the source so that you can cater to more clients, like in this particular vendor client scenario. So I don't know whether that answers to the question, but yeah.
Okay, thank you very much, Jogendra. And
yeah, thank you very much.
Thank you. And I think we'll move it to our next invited presentation. Yeah, with Sravanti. While Sravanti preparing her Zoom screen, I'm just going to quickly, briefly say about. I think Sravanti is a PhD, a Google PhD fellow, and pursuing PhD at Video Analytic Labs at the Indian Institute of Science. And recently, she has been awarded a prestigious Qualcomm Innovation Fellowship. Congratulations! And prior to this, she has worked as a principal engineer at SanDisk, and her research focuses on AI, machine learning, and adversarial machine learning and computer vision. It's over to you, Sravanti, when you are ready.
Thank you, Professor Ardendu. Am I audible and is my screen visible?
Yeah, it's clear.
Okay. Hello, everyone. I'm Sravanti, a PhD student at the Indian Institute of Science. It's my pleasure to present our work on efficient defenses against real-world adversarial attacks at the HPIV workshop here. Here's a brief overview of my talk. First, I'll be giving a background on adversarial attacks, on the adversarial threat model, on how we craft adversarial attacks, classification of attacks, and some examples. Next, I'll move to adversarial defenses, primarily adversarial training, single-step defenses, and our proposed adversary-free defense. And lastly, I'll be talking about defenses against real-world adversarial attacks, the proposed feature consistency regularizer-based defense, and I'll summarize the talk. So deep neural networks have been widely used in many computer vision and natural language processing applications and many more, and they've achieved near human performance on standard benchmark data sets, but they're not as robust as the human visual systems. Deep networks are prone to adversarial attacks, which are carefully crafted perturbations that can be added to images to flip the prediction of the model to a completely unrelated class with a very high confidence. For example, here on the left, we see the natural image of a hamster, and it is being predicted correctly by a deep network with a very high confidence. However, when we add a small amount of perturbation to this image, we get the image on the right, which looks very similar to the original image, but the prediction of the model has flipped to a completely unrelated class, which is a banjo, and the confidence of the prediction is also very high. So going to the formal definition of an adversarial example, it is defined as an input to a machine learning model that is intentionally designed by an attacker to fool the model into producing an incorrect output. And importantly, this does not cause a change in human prediction. While it's easy to check whether the prediction of the model has changed or not, the second criteria, which is the imperceptibility constraint, is hard to enforce. So in order to enforce this, we typically define threat models, which specify the conditions under which the attack is valid. So this acts as a mathematical proxy to ensure imperceptibility. This also includes assumptions about the adversary's goals, knowledge, and capabilities. So basically, it defines whether the attack is going to be a white box or a black box. So in a white box, typically for evaluating defenses, we consider the model to be a white box. That is, the adversary has access to the architecture and the weights, the trained weights of the model, and also the defense algorithm, so that very strong attacks can be constructed. And this leads to more robust evaluation of the defense. Commonly used threat models are LP norm-bound threat models and patch attacks, which we'll be talking about later. So here is how we craft adversarial attacks. We basically consider the loss of the network, which is a classification loss such as the cross entropy or max margin, with respect to the input pixels X. So here we basically maximize the loss with respect to the input, basically perform a gradient ascent on the loss. And we add perturbation, a fixed amount of the perturbation to the input image. So some of the variabilities in attacks are the loss which is used for the attack, such as cross entropy or max margin, what kind of noise we add before generating the attack, the number of attack iterations, the step size, and the number of restarts. So these are used to create different types of adversarial attacks. So here we'll define the LP norm-based threat model. So the amount of noise which is added to the input image, it is typically constrained within an LP norm bound of say a value epsilon. And this epsilon is selected such that when you add this amount of noise to the original image, the resulting image looks similar to the original image. So that is, the noise that is added should be imperceptible. So this is the LP norm based threat model. And the value of P and epsilon, they define the threat model completely. So here we look at some of the LP norm based threat models. In an L1 norm bound attack, we see that when this is the clean image and this is the perturbation which gets generated, the number of pixels which get perturbed are very few. So it's basically a sparse attack. Whereas when you look at the L2 norm bound attack, we see that it's concentrated within the region where the object is present, and the amount of pixels perturbed in the background are lesser. Whereas when we look at an L infinity norm-bound attack, every pixel is allowed to be perturbed by an equal amount. So the perturbation looks kind of uniform. Other types of attacks which are more common in real-world scenarios are the L0 attack, patch attack, and adversarial frame. So in L0 attack, we have a fixed budget of the number of pixels which can be perturbed. But the amount of perturbation of each pixel can be anywhere from 0 to 255. So this is the L0 attack. And in a patch attack, we define a fixed size and shape of patch, which can be added to the original image as an attack. So here it's a square patch of say 5x5 or 10x10. Typically around 1 to 3% of the pixels are perturbed. And here it's a more fancy attack where we are perturbing the boundary of the image so that it looks natural. So typically the real world adversaries are not restricted by these kind of threat models, but these are used for the purpose of building adversarial attacks and defenses. Here are some of the adversarial attacks which have been demonstrated in the real world. So in this example, it is shown that if we attach a 2-inch piece of tape at this tree in the speed limit sign, the self-driving car recognizes this 35 as 85, and so hackers can trick a Tesla into accelerating by 50 miles per hour by doing this. Here we see that we can trick a face recognition system by using specially designed pair of spectacles. So this can change the identity of the person to someone else. And here it has been demonstrated that by sticking some small black and white patches on a stop sign, it can be recognized as a speed limit instead of a stop sign. And here we see that by just rotating an image by a certain amount, this particular image is being recognized as a benign, as a malignant mole instead of a benign mole. So these can be quite dangerous in some of the critical applications, and this is one of the key motivation of building adversarial defenses. We now look at some of the attacks which are constrained within the L-infinity norm. So these attacks can also be applied to in case of real world attacks such as L0 or patch attacks. First is the FGSM, or the fast gradient sign method, where we use a single step gradient for construction of the attack. So here the loss is represented by J, which is a function of the output of the network, f of x theta, and the ground truth y true. So we take the gradient of the loss function with respect to the input pixels, compute the sign of the gradient, and multiply it by epsilon, which is the amount by which we want to perturb. So typically this is related to the threat model that we have defined. For example, here we are possibly looking at a threat model of L-infinity norm which constrained within epsilon. And this is added to the input image to generate the perturbed image. So another variant is the random fast gradient sign method, which is very similar to FGSM, but we add a random noise initially before generating the attack, and this makes the gradients more robust. Lastly, the PGD attack, which is a multi-step variant of the same kind of attack. So here we add a noise initially, and we again take the gradient of the loss, the sign of the gradient, and multiply it by epsilon step. But the difference here is we do this over multiple iterations. So this is a multi-step attack, and for evaluation, typically 100 or 1000 steps are also used. But for training, around 10 steps are used. So this is the strongest of all the attacks. We now move to the next section, which is on adversarial defenses. So the defenses are mainly categorized as input pre-processing based defenses or adversarial training based methods. So the very initial defenses which came up are the input pre-processing based defenses. So these defenses basically try to introduce some pre-processing layers before you pass the image to the network for prediction. So these can actually be non-differentiable. So these actually prevent the generation of strong gradient-based attacks, and they give a false sense of robustness. For example, something like bit depth reduction or JPEG compression of the image before you actually pass it to the network. So this doesn't involve any computational cost during training, but subsequent works have shown that these defenses can be broken by creating some differentiable approximations of these non-differentiable layers. So the backward pass differentiable approximation and the expectation over transformation attacks, they have been able to break these input pre-processing based defenses. And there is no existing defense which actually works in this category. So after this, some of the multi-step defenses came up, and these actually use strong multi-step attacks for training. So in every iteration of training, we generate strong multi-step attacks and use those perturbed images for minimizing the cross entropy loss. So it's a min-max game where you first maximize the cross entropy loss for generating the attack, and then you minimize the cross entropy loss on the same for adversarial training. So PGD adversarial training performs exactly this, and this was like the first multi-step defense which was successful. These actually achieve state-of-the-art robustness, but they have high computational cost because we require a lot of forward and backward propagations for the attack generation. So it's around 11x, the training cost is around 11x higher. Then we have single-step defenses. So single-step gradients, like the FGSM attack that we have seen earlier, they are used for training. And this trades off the performance with the computational cost. But the problem with single-step defenses is gradient masking, which leads to a false sense of security. So basically, if you visualize the loss surface of the model which is trained using single-step adversarial training, it's very convoluted. So at the input image, the gradients are very different from the vicinity of the image. So this prevents the generation of strong single-step attacks. And because of this, the training becomes weak. So this leads to models which are not robust to strong multi-step attacks. So we try to, since the amount of computation which is required for this multi-step adversarial training is quite large, we try to answer the question whether we can achieve adversarial robustness without the use of adversarial samples during training. So in this work, which was accepted at CVPR 2020, we take a clean image and we quantize it to generate this quantized image, and we pass both Xi and Q of Xi to the network in a single batch. And then we impose a regularizer on the pre-softmax values of Xi and Q of Xi. So the overall loss function which is used for training is the cross entropy loss on the clean images and a squared L2 regularizer between the pre-softmax values of the clean and quantized image. So the cross entropy loss ensures that both the coarse and fine bit planes of the original image are used for prediction. And this regularizer, it ensures that the network produces consistent outputs when you give the full clean image or when you give the quantized image. So this actually leads to adversarial robustness to L infinity attack. So as we can see here, the proposed method gets a significant boost over the standard training and input pre-processing based defenses, significant boost in robustness, and it's also comparable to multi-step training methods at a much lower computational cost. We now move to the third section, which is on efficient defense against real-world adversarial attacks. So the existing defenses are mostly focused on L infinity and L2 based threat models, mainly because they're easy to optimize the attack generation. But if we look at attacks in the real world, they're mostly sparse attacks because they're easier to implement in the real world. Like for example, when we look at an L infinity based attack, it tries to perturb every pixel by a very small amount. And this is difficult to implement in the real world. Whereas if we look at patch attacks, they change only a small part of the image, and it's very easy to print that small patch and stick it on say a stop sign. One of the challenges with generation of sparse attacks is that they are computationally more expensive than the standard L2 or L infinity based attacks, because every pixel in say a patch attack, it needs to be perturbed all the way from 0 to 255. So it requires many more attack steps. So the multi-step adversarial training methods of sparse threat models, they require much higher computational budget. So standard adversarial training is more expensive in this case. And the third aspect of real-world attacks is they need not be restricted to a single threat model. Because a real-world adversary is not restricted to any such threat model. So it's important to for such defenses to generalize to unseen threat models as well. We consider the goal of achieving adversarial robustness against sparse attacks. We consider patch attacks and L0 norm-bound attacks efficiently. And we also look at how these defenses generalize to unseen attacks. This is one of the prior works for a defense against patch attacks. So here, basically, the attack, first of all, the patch location optimization is performed by doing a greedy search over the entire image. And this is again an iterative process, which is computationally expensive. And even the patch generation, it involves around 30 to 50 steps of optimization. So after this, the attack is generated, and then the minimization is done for training. So basically, this involves a lot of additional computation for both identifying the patch location and also for computing the attack at the identified location. In our work, we try to extend the same framework of our CVPR 2020 paper to basically generate defenses against sparse attacks. So this is the feature consistency regularizer framework, where for every clean image xi, we pass two other images to the network. One is a cutout based augmentation, which blanks out a certain portion of the image. And another is a patch attack, where we place a random patch at a random location on the image. So this random patch is generated by just sampling every pixel from the range 0 to 255, adding it to the original pixel intensity level, and then clipping it to 255. And these three images are passed to the network, and we try to enforce consistent feature representations between the cutout-based augmentation and the perturbed image. So our final loss is a combination of the cross entropy loss, which is again a convex combination of the cross entropy loss on the clean image and the cutout based augmentation. And we also have this feature consistency regularizer, which tries to enforce similar pre-softmax values for the cutout based augmentation and the perturbation. So this is a squared L2 norm based regularizer. So we have three variants of the proposed defense. One is FCR-RL, where we do this random attack at random location. So this actually requires 0 additional forward props for location optimization and 0 additional forward props for attack generation, because it's all random. And this performs comparable to the existing defenses, which actually use multi-step optimization for both location and the attack. And we improve on this using a single step gradient for location optimization in alternate training iterations. So in this, we have an additional computational budget of half forward and backward prop per iteration, since it's in alternate iterations. And we achieve a significant boost in robustness using this. And the third variant is basically to use the single step gradient for both location optimization and attack generation. So here we have an additional 0.5 budget even for the attack generation, and it again achieves a boost over the prior two methods. And although this is a single step attack, we avoid the problem of gradient masking, which was discussed earlier, by using random attacks in alternate training iterations. So we still have that amount of robustness, and the network is not able to go to this solution where the loss surface of the network is gradient masked. So that's how we avoid the problem of gradient masking. And then we try to see how well the proposed defense generalizes to unseen attacks. So we perform the training on using patch attacks of size 5x5. And we see how it generalizes to say 2, 3, 4, 5, 6 squares. So that we keep the total budget same, around 25 pixels. And we also see how it generalizes to a different shape attack, which is rectangular, and how it generalizes to L1 norm or L0 norm based attacks. Now, if we compare the average performance across these unseen attacks, then the proposed defenses, they outperform both the certified defenses and also the existing multi-step based defenses at a much lower computational cost. We also show that the proposed framework can be used for robustness against L0 norm bound attacks. So the three proposed attacks are able to outperform the PGD 080 at a lower computational cost. So to summarize, we propose feature consistency regularizer based training and three variants based on random location, gradient based location, and single step gradient based location and attack. And the proposed defense generalizes better than existing empirical and certified defenses to unseen sparse attacks such as multi-patch and L0 norm-bound attacks. And we also achieve a boost in robustness when we combine this proposed framework with the state-of-the-art certified patch defense, which is BAG-cert. And the proposed framework can also be extended to other threat models such as L0 norm. So I would like to thank my collaborators and co-authors of all papers and my advisor, Professor Venkatesh Babu. And I also thank the organizers of the workshop for giving me an opportunity to present my work here. Here are the references, the two papers that I have presented. Thank you.
Thank you very much. Okay, well, I can pose one question. I think we're a little bit of time. Did you identify what kind of attack is more serious than other type of attacks? Is your model able to kind of find out which type of attack is more problematic or difficult to detect?
You mean, is the defense able to detect which one is more problematic?
Yeah, more.
Okay, so there are defenses which try to have this reject option as well. So those kind of defenses would do that. But here, the defenses that I have presented here, they only have a standard classification option. So there is no option that, okay, this attack is strong and I'm not able to predict it, so I'm going to reject it. So that option is not there in this, but it's always possible to train a classifier and a detector as well.
Okay, thank you. I think I'll take one more question from the audience. Does the adversarial attack reveal that the extracted features are not robust due to the perturbation of the original image?
Yes, definitely. The vulnerability of the model is revealed based on the adversarial attacks, and so when we do standard training, the network basically relies on some weak correlations that are present between the images of different classes and the class labels. So adversarial training is what prevents it from having such non-robust features, and the network is able to focus more on robust features instead.
Okay, thank you very much.
Thank you.
Okay, so now we're supposed to be starting the paper presentations at 40, but still we're 5 minutes delay. We're doing well. We're not that that bad. We're 5 minutes running late. So what we are going to do is, could you please let us know the presenter next 3 papers, just who is presenting? Just send a message to me or in the type in message in the everyone. The next 3 papers, one is robust 3D object detection for moving object based point pillars. Second one is weakly supervised free space estimation through stochastic co-teaching, and third one is attention augmented real-time 3D object detection. So if you could let us know and about the presenter, then we'll plan accordingly. And it is a short break. I would say 5 minutes, 5 to 7 minutes. So we'll see you around 150. Yeah. Okay. Yeah, we'll see you in 150, and then we'll take it from there. Thank you. See you in a bit. Hello, welcome back, and I'm going to pass to my co-organizer, Young Hai Liu, to talk over.
Hello. Good morning, everyone, or good afternoon, or good evening. It depends where you are. So let's move on to the purpose session. In this session, we have altogether 3 papers and 1 keynote. So for the paper sessions, please do try to follow the time. In this case, 10 minutes for presentation, 5 minutes for question and answer. For the keynote, it's expected to spend 40 minutes for presentation and 5 minutes for question and answer. Okay. So the first paper is titled Robust 3D Object Detection for Moving Objects based on PointPillars. The speaker is Ryota Nakamura. Okay, thank you. Let's enjoy the talk. Please start when you are ready.
Okay.
Yeah.
Thank you. Hello, everyone. My name is Ryota Nakamura from Kyushu Institute of Technology, Japan. Today, I'd like to talk about robust 3D object detection for moving objects based on point pillars. In recent years, automakers have been active in development of autonomous driving systems and advanced driving assistance systems, both of which essentially require high accuracy recognition of the environment around a vehicle. Within this context, various objects, for example, vehicle, cyclists, pedestrians, detection techniques are being studied. This table shows some typical sensors for autonomous vehicle: camera, millimeter radar, and LiDAR. Generally, those sensors are utilized to perceive traffic environments and to detect objects. Because LiDAR can obtain the information of distance to the object and 3D shape data with high accuracy. And it is also robust against environment changes, such as various lighting conditions and weather conditions. So in this research, we focus on object detection method using LiDAR. While object detection from video images and LiDAR with deep learning have been observed to be continuous and stable, there are times when a few continuous frames suddenly go undetected, thereby resulting in a phenomenon known as a momentary misdetection, we called MMD, as shown in these images. Verifying and resolving its cause should allow us to improve overall detector accuracy, thereby producing a safer system. We examined the cause of these MMD by utilizing VoxelNet, which is one of the well-known techniques as a recognition method for 3D point cloud using deep learning. The fourth of this paper in the following MMD. MMD is a phenomenon in which objects that have been detected currently over time in most frames is undetected for one frame. In case of MMD in camera images, the 2 factors triggering MMD was defined as being transition between the anchors used from either position changes due to detected object movement or scaling changes. As shown in this slide, in the camera images, the size of the object in the image data changes depending on the distance between the camera and the object. However, due to 3D point cloud features, the size of the object in the point cloud is independent of the object's position relative to the LiDAR sensor. Therefore, we focus the target object's position relative to the sensor position. VoxelNet extract feature from segmentation of input point cloud by 3D voxels. Verification of the cause of MMD checks the changes in the detection score for the target object when the reference point for segmentation changed. The movement direction and distance are as follows. Segmentation size in XZ axis of 20 centimeter, 1 centimeter intervals from -20 to +20 centimeter along each direction. Segmentation size in y-axis of 40 centimeter, 2 centimeter intervals from -40 to +40 centimeter along each direction. The result was as follows. The horizon axis in the movement distance and vertical axis is the direction score. As a result, the detection score improves in almost missing frame. From those results, we can see that for most of the missing frames, the detection score is improved when the frame is moved about half of the segment area. Based on these results, we confirmed that the cause of MMD in VoxelNet was associated to the position of the target object in relation to the voxel. We report on our proposed technique for detection objects in a 3D point cloud, which extended the technique based on our last research. On this research, we examine PointPillars, which is based on VoxelNet. PointPillars provides a good balance between prediction accuracy and processing speed. One feature in VoxelNet are extracted per voxel features in PointPillars are extracted per pillars and then reduced in weight using two-dimensional convolution. Because it provides a good balance between processing accuracy and processing speed, PointPillar will likely see future use of technique, future as a technique for detection objects in 3D point cloud. With a point in mind, are given a cause of MMD that described in last research, we proposed object detection technique. So as shown in this following figure, we propose that the accuracy can be improved by adding features extracted from the segment with reference position for segments moved in each axis direction to the future extracted from the different default segments. From our last research, the reference point for segments were changed in order to change detect object position relative to the segments, thereby confirming that the detectable object was present. The segment reference position was shifted at the distance of half of the pillar size. For this reason, the method proposed for this study changes a reference point upstream in the network before incorporating the 3D point cloud feature. More specifically, the network structure of the network PointPillars backbone was changed as shown in the following figure. Our examination is a key object detection benchmark test set, which consists of 3D point cloud data derived from in-vehicle LiDAR, camera images, and driving data. It also includes label for the object detected. This data set has 3 annotations: car, cyclist, and pedestrian. The data values are categorized as hard, moderate, or easy according to the object size and the level of overlap. Our experimental results are shown in this slide, where that can be seen that the average precision was confirmed to improve in nearly all of the categories for car cyclists and pedestrians. Accuracy was especially improved in our proposed technique number 1 for cyclists pedestrians. Our number 2 was experimented to check the change in processing speed by reducing the number of backbone and detection head features. However, its results were not significantly different from those of our number 1. That is because the point cloud in this process chain task the most time to pre-process. So increasing the input point cloud set seriously slow processing speed. At the present stage, the processing speed is reduced due to the simple configuration of the network. But we think that the processing speed can be reduced to the same level as the original method by running the network that extracts feature from point cloud in parallel. As seen in this first figure A, B, C, it was also confirmed that the proposed technique could detect objects that were undetected with the point pillars. That the first positives, such as a dumpster detected as occur in figure D, were correctly removed. From this result, it was considered to be more effective to change the segment reference position and add surrounding data as features instead of changing in single segments. In this paper, we proposed robust object detection techniques for moving objects from 3D point clouds. As obtained from in-vehicle radar based on the case of MMD, as defined in our last research. Set multiple segment reference position for the input point cloud and extract feature from each position. However, in our proposed technique, the processing cost increase due to the simple configuration of the network. In future, we plan to quantitatively test whether the MMD found in our last research also occur in point pillars, and whether or not the proposed technique can limit those MMD. Thank you for listening.
Thank you. Yes, your time is well controlled. Thank you. So I think the topic is very interesting about how to improve the detection of the object, especially in the real driving environment. So any questions from the audience? So one question received from the audience is about what type of backbones has been used in the model. Hello? Rioter?
Oh,
one question is about what types of backbones has been used in your model for the object detection. Coordinate paths or something? What is the baseline network?
Backbone is backbone is a simple 2D CNN.
Okay. Okay. Yeah.
Sorry.
So in this case, then how did you obtain the 2D like representation of a given point cloud? So in order to apply 2D CNN, you must change the point cloud from 3D to 2D representation. Yeah.
Sorry, can I ask you to type a question into the chat?
Sorry, essentially the point cloud is a representation of the object in 3D. In order to apply 2D CNN, you have to represent the 3D point cloud in 2D. So then how did you do that?
Oh,
Or did you consider some like just sections of the point clouds?
oh. Oh.
So essentially, how did you represent the point cloud in 2D space?
Spice. So,
Then, or in other words, how did you apply 2D CNN to 3D point cloud?
so sorry, but it's difficult for me to answer your question in English now. But if you email me later.
Yeah, you did, yes, you did. Yeah. I don't know, yeah. Yeah, from Addendo, yes, probably yes, it's better to take this offline, and you can just email us the speaker yes, about the question, and hopefully, yeah, all will respond. Yeah. Okay, thank you. So, okay, let's move on to the next paper. This paper is entitled Weakly Supervised Free Space Estimation Through Stochastic Co-Teaching. The speaker will be Francois Robinet. Okay, please start when you are ready.
Yes, I just need to give Zoom permission apparently to share my screen, which might take just a second.
Okay, I think that you should be able to share your screen.
Yes, yes. I should be. I just have to quit the call and come back. Just 1 second. Sorry.
Okay, yeah, no problem. Yeah.
Okay, this should now be good.
At the bottom line, you should be able to see yes, the share screen button.
So you're able to see my screen now, right?
Yes, indeed, yes. Okay.
Okay, okay,
It's
perfect. Thank you for your patience. All right, so hello everyone. My name is François Robinet, and I'm a PhD student at the University of Luxembourg. And today I will be giving you a presentation about recent work from colleagues and I on the topic of weakly supervised free space segmentation. So in this work, we are considering single images taken from a road-facing camera that is placed in a moving vehicle. What we are doing is we are attempting to classify every pixel as either free or occupied space. And for evaluation, what we have used is the popular Cityscapes dataset, which provides around 3,500 finely annotated frames, so frames for which we have annotations, pixel-wise annotations. So out of these frames, we use 500 for testing, and the rest is used for training and validation. So as is typically done for evaluation in segmentation scenarios, we have to distinguish different types of predictions, as is illustrated in this example. So here green represents correct predictions, red represents incorrect ones. Missing regions are annotated in orange at the back of this road here, for example. And one specificity of this problem is that Cityscapes also has part of the images that are not annotated as either free space or not free space, even though as humans we can decide it's not always obvious. So these regions are ignored at evaluation time, and they're annotated here in blue. So one example of this is the hood of the car. At the bottom of every image, we can usually see the hood of the car. And that is technically maybe occupied space, but it could also be considered free space, since technically you can drive on it when you drive on it, the car moves. So these blue regions, they are ignored at evaluation time. So our metric of choice is, as usual, IOU, which is free intersection over union. So correct predictions of free space over all predictions of free space, correct and incorrect ones, plus the missing predictions. We also report precision and recalls in the paper, but I omit them here for the sake of brevity. Okay, so since we have ground truth annotations in cityscapes for all the training frames, the first possibility would be to use a fully supervised approach. So there you start by training a segmentation model and you use ground truth predictions and you use a very traditional training loop with, for example, a binary cross-entropy loss. And if you do that with an architecture, so what we used is a UNet architecture based on a ResNet 18 backbone. And if you do that supervised, you are able to achieve good results with 94% IOU. But this is not the focus of our work, because we know fully supervised segmentation works well, but it has several drawbacks. So among those drawbacks are the fact that pixel-wise annotations can be very expensive. It's impossible to annotate data for all variations in the environment, because we have different countries, road types, weather, illumination conditions. There is the problem of having an unannotated data set from the start. So the question is, can we train such a detector with little to no labeling efforts? There is prior work from Tsutsui et al. That showed that even without human annotation, what you can try to do is generate weak labels. I won't go exactly into the technique they use to generate these weak labels, but it's based on extracting features from a pre-trained image classifier that was trained on ImageNet. You extract those features for every superpixel in the image, and then you cluster the superpixels together. And if you use this technique, you're able to achieve an IOU of 79%. So this is prior, which we build on. And one problem with these weak labels is that sometimes they fail catastrophically. So you have an example here, an image that doesn't look particularly challenging, but where the weak label generation technique fails completely. So the question is, can we use those weak labels, but train a model to generalize better from them? So if you take this approach, you basically train now the same units that you were training from ground truth before. Now you will be training it from weak labels instead of the ground truth. So the ground truth is now imperfect. You can consider it as a noisy ground truth. And then if you train a model on that, you can see that you reach an IOU of now almost 2.5% better than the raw weak label. So the model is indeed able to improve in generalization performance, even though it's trained on noisy ground truth. It's able to improve over the noisy ground truth itself by 2.5%. So now the question is, can we do better than that? And the idea is that we can do better if we take into account the fact that the ground truth we are using has noise in it. And this is the intuition for stochastic co-teaching. So there are basically three intuitions. The first intuition is that models tend to learn easier patterns first, and this was shown in this reference here. The next intuition is that noisy labels tend to be harder to fit because they are noise, and patterns that don't exist tend to be harder to fit usually. And therefore, they are more likely to incur eye loss, at least at the start of training. When the model knows nothing, it has a hard time fitting noisy labels. So the idea there is that if we reject high loss samples, what we should reject the most is noise, actually. And in our paper, we show empirically that this holds for our problem, where this is the loss distribution and this is the density. And you can see that at high losses, you tend to have a higher fraction of noisy examples than at low losses. Okay, so here on the tail end, it's almost all noise. And so based on this idea, what we use is stochastic co-teaching. So we propose an adaptation of the existing co-teaching, which is done for image classification. We adapt it to a segmentation problem that we have here. And so the way stochastic co-teaching works is that you have two networks. They don't have to be the exact same architecture, but they could be. They are independent. So if you use the same architecture, you have to initialize them with separate weights. And then you give these two networks the same batch of data, and each student network computes their own pixel-wise loss in steps A and B. And then in step C, what you do is that each student samples a given subset of pixels with probability inversely proportional to the loss. So this means we are preferably sampling pixels with low loss, and these pixels are more likely to be clean because they incur low loss. And then what you do is that you exchange, each student exchange the sample pixels that they deem to be clean. And each student then trains only using the pixels that the other student has selected to be relevant. So this is kind of similar to how two humans could teach each other by selecting the more relevant examples for each other. So applying this technique of stochastic co-teaching, we are able to improve over standard training. So standard training would be just training out of the weak labels without taking the noise into account. So if you do stochastic co-teaching, you're able to improve slightly over this result. And then if you, because you have trained now two models in stochastic co-teaching, you end up with two models. So what you can do for free is basically just ensemble them. And if you ensemble them, you get another slight performance boost as we've seen. So to conclude, so our work adapts co-teaching for segmentation tasks and uses it for free space segmentation in particular. We introduced stochastic co-teaching, and we showed that it more effectively filters out label noise in this task. So our best model compared to the fully supervised baseline, which uses the ground truth, it reaches 87% of that IOU, 93% of the precision, and 93% of the recall, while using no human annotations at all. So in the paper, we also analyze the impact of co-teaching schedule and the convergence of students, as well as some limitations of this approach. So for future work, we suggest to consider the output of our trained model as stronger weak labels, because we're able to refine the weak labels. Maybe we could use those stronger weak labels as the weak labels in a second training step and follow this iterative training procedure to iteratively refine weak labels and further improve performance. Another thing is that here we propose co-teaching. Originally, it was proposed at the image level, and what we have done here is that we've proposed to use it at the pixel level. But it would also be interesting to investigate its use at the object level, so somewhere between the image level and the pixel level. So for example, there you could investigate in applying co-teaching on superpixels rather than pixels. And finally, we would like to investigate the performance of this method in the more general setting of semantic segmentation, rather than just restricting to free space segmentation. And that is the end of this presentation. I thank you very much for your attention and welcome any questions. Thank you.
Thank you. Yes. Good timing for your talk. So clearly, segmentation is so important for the understanding of the environment for driving or something. So any questions from the audience? One question from Adendu about how much noisy levels is your model can take without a significant degradation of performance?
Yes, so this is not something we have completely investigated. What you could try is artificially degrading the performance. So the noise we have in our data comes from the fact that we generate weak labels without ground truth at all. So we are simulating basically a setting where we don't have ground truth. So it's hard to know what is noise and what is not noise. But what you could do is take the ground truth and artificially add some levels of noise and investigate how that impacts the model. For co-teaching in particular, this has been done for classification, not for segmentation. So I cannot answer the question for segmentation, but for classification, it's robust for even pretty high levels of noise, even like imagine 30%, 40% of noise. Here in our case, the weak labels we use here, oops, too far. The weak labels we use are far from perfect, right? They only reach 80% or 79% IOU, and still there is a lot of noise in there, and we're able to filter some level of that noise, but of course not all the noise. Otherwise, we would reach the same performance as the supervised approach, which we don't.
Okay, thank you. I have one question. I think you've got like two networks, and then you create some clean labels, and then you let the network to learn the clean labels from another network. So did you do some kind of like comparative studies between this proposed co-teaching and then the direct learning of the network from the clean labels themselves?
Yes, so you're, if I understand correctly, you're asking basically why use two networks, right?
Exactly.
Why not just train from one?
Yeah, indeed. Yeah.
So yeah, yes, okay. So you could try that as well in the paper that proposed co-teaching for image classification. This is a question they try to address as well. It works. It doesn't work as well if you just use a single network. One intuition for this is that if you have two networks and they select clean indices for each other, you're in some sense avoiding the problem of overfitting your initialization as well, because basically the initialization you have will determine the loss you incur at early iterations, right, for each indices. And so at the start, this is kind of random, and having like two initializations, selecting independently clean indices and having them move samples across, but keeping each weight on each student still helps with training. This is kind of like imagine a human trying to teach himself something, and he selects himself the exercises maybe that he thinks are more interesting. This can work, but also having this diversity coming from someone else pointing to you, which sample seems interesting for him, maybe also interesting. So this is kind of a diversity argument there. Yes.
Good. Interesting. Yeah. Thank you for your talk. Yeah. Okay.
Thank you.
Thank you. Yeah. So let's move on to the third paper, titled AI 3D Net Attention Augmented Real-Time 3D Object Detection. The speaker is Abhinav Saga. Is Abhinav here? Hello? Hello?
I don't think so. The speaker is here. We can move into straight to the keynote speaker. I think this particular speaker is absent.
Okay, that's fine. Yeah.
Okay. Thank you.
Okay, it seems the order of the third paper is not here. So let's move on to the keynote talk, entitled "Towards Self-Driving in Unstructured Environments." The talk will be delivered by Professor Jawahar. Professor Jawahar is a dean and Amazon chair professor at the International Institute of Information Technology, Hyderabad. He received his PhD from IIT Kharagpur in 1997. After that, he worked for Center for AI and Robotics, Bangalore till 2000. He joined IIT Hyderabad in 2000 to initiate a research group focusing on visual information processing. He recently awarded the prestigious ACM India Outstanding Contribution to Computing Education. He is associate editor of PAMI and a chair in many computer vision conferences. It's our pleasure to have you as a keynote speaker in this workshop. Okay. Let's enjoy the talk.
Thank you for the kind introduction. I hope you can hear me.
Yes, indeed. Yeah, that's fine. Okay. When you are ready, you can share your screen, or
yes,
just start. Yeah.
Yeah. Can you see my screen?
Yes, indeed. Yes, we can see your screen. Yeah.
Yes. Okay. Yeah, thank you. So for the kind introduction, I'll talk about some of our explorations in driving safety in the smart vehicles or intelligent vehicles or even normal vehicles in the present like the Indian unstructured environment. That is our where we have been trying to do some explorations. To start with, so we had seen a lot of development in the area of perception. And if you look at the perception problems in the structured world to the unstructured world, I'm sure as a computer vision researchers, we can see a number of interesting challenges. The density of vehicles, their movement patterns, the diversity. So this is very easy for us to observe at this stage. And this makes the technology penetrating, the technology getting employed in the unstructured environment very poor, and the development itself becoming very challenging. Not only that, so it is this sort of like a crowded urban pictures are known to all of us. Even if you go to the rural areas, you start to see the challenges associated with visibility. You also see the challenges associated with the narrow road, lack of road boundaries, multiple participants sharing the road boundaries, and a number of issues which face, like where to go, how to go, where to go, the lack of signals, lack of tools, so this all make the technology are working reliably diverse in unstructured environment. Now, if you look at the statistics, we see that the road is not very safe, even for human drivers. Large amount of death that result in GDP loss. Now, is there anything that we can do to minimize this? If you look at what happened in the initial months of COVID, we saw suddenly there is a big reduction. And indeed, this has nothing to do with technology. We saw that this reduced only because of, so there is a positivity possibly painted or at least thought for a while. And we know obvious reason, it is not anything other than the lockdowns, the less traffic, the reduction in people moving. This is not the way. So and now we are back to more and more normal. And we are seeing the death tolls, the accidents increasing back to the old numbers. So we know that this is why this is the reason. So we want to understand, so this unstructuredness, how does it matter to us as researchers? How does it matter to the technology that we care? How does it matter to the technology that we are work on? Far more, why is this happening? So why this sort of issues are coming up? So we want to possibly understand the root causes so that we also appreciate what type of solutions are required. So to answer a quick answer to this question is like, if you know that this unstructuredness is going to be a problem while the technologies are not reliably working in this world of unstructured traffic or movement patterns or surroundings. So the one obvious answer that we know is there is a complex prior, which is not very easily available from, say, well-structured highway traffic, road traffic data set that are captured in the Western road. is not going to work here because a models or say today's machine learning models that are trained on such data sets are not going to directly extend to this. So what is required if you want to address this issue? Okay, so let's come back and ask the question, what we care at this stage when we are looking for technology in this space. We worry about if you want to improve safety, if you want to develop technology for the roads, we need technology that helps in driving, the technology for vehicles, technology that helps drivers, technology that helps driving. That's only one part of the story. There is a second piece that is the human aspect. So we also need to educate people. We need to have a mechanism that the rules, regulations, and practices can be enforced. We need to worry about how this technology interface with humans with different cultural issues, language issues, and different priorities, the social issues in adaptation of such technologies. Then the third dimension that is very important for us to appreciate is the infrastructure. We assume that vehicles are available or vehicles can have technology, assuming that infrastructure is available. The infrastructure is limited and it's possibly far more costly than the other two dimensions. How do we effectively use our infrastructure? And a country like India, the infrastructure is huge and maintenance of it or upkeeping of it, keeping the required like a quality is really, really challenging. So these three dimensions we have to look into. So in this talk, I'll possibly touch upon some of these issues of in all these three dimensions. If you are talking about safety, if you are talking about safety of citizens, if you are talking about safety of vehicles, if you are talking about improving the life in this unstructured environment. Just to recap, so we all understand that the machine learning story. So one lesson for us is all about is your solution that you build is only as good as the data that you can have. So if you're designing solutions in one part of the world with one type of like a data sets, then you are possibly going to struggle to adapt into this sort of situations. And of course, this is quite clear. There are machine learning way of looking at it in transferring the knowledge, working across these domains. But one very important is also to understand what this data set is going to be, what this new world is going to be. So one of our first explorations in this area was to create an India driving data set itself. So the first attempt was to create a small data set that possibly makes the entry into this feasible. So if you look at the technology development in this space today, the data sets have made it say the entry barrier to be low. So it is possible for, say, many students to play with it, many startups to try the technologies, many researchers to try their algorithms that are developed elsewhere also to try on this, and also appreciate the challenges, why the performance metric, say recognition or segmentation or classification, whatever you may want to detect or whatever you may want to measure is different from the rest of the world, and what changes are required. So this was what the first phase of it enabled. And of course, we are in the process of extending the set. So today's versions of this IDD has far more number of images than what we have mentioned in the previous video. Not only that, so this is not enough if you really want to test develop the local technology and enable an ecosystem around this. So the next attempt was to set up a platform that is available for people. It is impossible for small startups and small universities to have their own car platform for experimentation. So looking for a mechanism where this sort of frameworks are available or this sort of infrastructures are available for people to come and use it and develop technologies, validate technology and deploy technology and get a feel of it. And even for researchers who do not have access to such challenging world surroundings and testing the feasibility of the technology. So this provides a mechanism of even remote access. So this is where so we hope this sort of mechanisms, availability of data sets and availability of such platforms, democratize the technology development and spread in the country in different form. So these data sets have been growing with different type of modalities, different purpose, in multiple directions, including things like we would like this data set to be useful or possible for students to play with on their own laptops, maybe a small exercises that they can do. We can talk about like a low memory compact model developments. We can talk about multi-model data sets. Of late, now we have been also creating or extending this IDD with more, say, 3D point cloud and other annotations. Some of them are going to come very soon. So this data set and the popularization and also enabling people to develop, validate, verify technology is one part of the story. So let's come back and ask the question, if it is unstructured, and how does it matter? And we saw some answers. How as a machine learning computer vision research is what we need to do. Why does it matter? Why this unstructured appears? So one important answer is the socioeconomic situation that lead to challenges in enforcements, poor infrastructure and maintenance, which lead to these unstructured situations. If you look at the road networks of a country like India, we see there's a huge percentage of the road network is rural roads. And they are managed by different agencies, possibly do not have sufficient like a financial, say, power to maintain in high quality, because there are higher priority items than this. So if you look at the solution that we use for improving the safety, like CCTV camera based solutions that are popular in the urban areas, they are very, very costly. And if you look at your the traffic violations are happening elsewhere, while CCTV cameras are in the urban area. So what we need is solution which is possibly cheap and possibly scalable with some level of effectiveness. Not only that, the poor maintenance of it. So how do we detect objects of poor maintenance and how are they visible? So visibility of such things, what type of maintenance are required. See, if you want to even take an audit of the road infrastructure for a city, it is quite painful today because most of the time this is done by humans. Humans traveling, humans validating, humans checking, humans reporting, and finally leading to a set of complaints or set of possible changes that gets done, that gets maintained by a set of people later. Say, for example, if a street light is not functioning, it takes time to get it sometimes fixed because it needs to be brought into the attention of the right assault authority. How can some of these be more automated if citizens can participate and if citizens can provide this information, and if we say simple visual stream can provide reports of this sort of audit? So here is something that we looked at a couple of years back when we had a flood in our city. And we were talking about, like, can we detect the damage, or can we measure the damage, or what happens to the city after a flood, where all the damages happen, where all the water gets logged, and where all the attention is required, with a simple video stream obtained by driving a car through the road network of a city. So here is an example. So for example, like the problem is casted as a semantic segmentation, which tells us what type of damages exist and where does it exist on a map, so that the appropriate attention can be brought. So the technology that possibly developed for autonomous navigation gets help at a different level, where it is good help in maintaining a better road infrastructure. Not only that, what type of roadsides around, say, objects, or the trees exist, what type of obstacles exist, what type of maintenance is required. Can such things be captured? Even not only even a car, can we do that with simple, say, two-wheelers? So here's an example of how the two-wheelers based a simple audit can give you a report of what is there in the tree, deforestation, greenery metrics of cities can be measured with ease. How do we use such simple video stream be useful for detecting, say, traffic violations? And where these violations of, say, two-wheeler violations, three-wheeler violations, which are very, very popular, because people see, if there's a vehicle going, why don't I have more than one or two passengers on that, so that you can save the cost? So the cost is, and affordability, etc., will become very, very important factors for people when they travel. And how can some of these be done with simple video streams? And there are a lot of government vehicles, there are a lot of public transportation, like a vehicle which run around in a city, and they can provide the video stream which can tag such potential violations which are presently possibly detected primarily or only from the CCTV cameras. So we talked about unstructured. Now let us go down still further. So we saw the people need we need solutions which can look at infrastructure, which can look at traffic violations, which can be captured from simple mobile phone cameras, etc. So now we say we eventually want this not only like a capture and issue challans and issue punishments and fines, etc. That is one part of the story. But we also should see how this technology can improve the safety of, say, cities or urban areas or villages at scale, and how can we capture the present state and where we need the changes to be made. So here's an attempt which we have been carrying out of recent time.
Advanced Driving Assistance Solution, or ADAS, will offer an economical way to enhance safety of fleets and road users. ADAS alerts, alongside driver assessments and training, can notably improve driver performance. Mobility analysis will monitor dynamic risks of the entire road network to define grey spots. Preventive maintenance of such risky stretches will prevent black spots before they claim lives. Infrastructure safety will design engineering fixes for existing road black spots. Continuous monitoring will also deliver improved ROI of road infrastructure maintenance. Join us in the mission to reimagine road safety with the predictive power of AI. Project iRaste, intelligent solutions for road safety through technology and engineering.
So this is a pilot that is undergoing today in Nagpur, a city in India, in the center of the city, where we look at, so if you look at this, the picture on the right side, So we had seen a lot of interesting discussions on the layer, the bottom two layers, the technologies for autonomous driving and technologies for ADAS. And we can talk about like how the development in one is helping the other and how these two are highly connected because both of them are integral part of the same industry in some form or other. But we can also look at another way that how can the technology that developed for say something like ADAS can be useful for improving the road safety? How can we use this sort of data like say for example the alerts and where the alerts happen, why the alerts happen, and how do we use it for understanding the road network where the potential maintenance are required, and how can such data be useful for like improving the network itself or providing say civil engineering or road engineering solutions? How can we use it for improving the driver training, and how can we thereby say reducing the accidents or potential warnings? And this was experimented on a number of public vehicles. A number of signals that are available are captured, and their distributions, their statistics are studied over time and understood where the fixes are required, what are the trends, which regions require actions, which regions require attention, and what type of changes are required. In a way, this provides the ADAS technology provides huge amount of data on which the road safety solutions could be designed. So not only that, so we also have situations where, so we talked about the participatory solution. So you can deploy such solutions or the devices on large number of vehicles and providing us data, helping us planning the city and improving the safety over time. Now, if you look at the unstructured, again, coming back to the question that we have, why is it? And how do we care about it? What do we care about it? These socioeconomic situations that demands not only the city level maintenance is very, very important, but now when you come back to the individual vehicles or individual riders or the drivers, they also demand low cost solutions or even zero cost technologies. So everybody is keen on improving the safety, but who will pay for it? So we need solutions which are possibly much simpler to deploy. See, if you look at, this is where the issues of, say, role of smartphones come into the picture. A country like India has huge penetration of communication devices, smartphones. How can individuals or smartphones that people carry in the vehicle, whether it is a two-wheeler or a three-wheeler or a four-wheeler, help in improving the safety? What are the roles of citizens? And how can this AI in terms of personalization and adaptation? And one starting attempt was to look at what is say, for example, with such a device, if you have a mobile phone mounted in your car, can I say how good is the driving? With cameras on both sides of such a device, can I monitor the driver? Can I look at the road? Can I say that what is the safety index of the driving? See, nobody drives. There are multiple reasons, say social, cultural, cost, and many other reasons for people to say start not wearing the seat belt, not driving, not following the lane disciplines, and many other things. And how do we rate? How do we build such indices so that there is a history gets done, and then you know what is safe driving, and you can incentivize the safe driving so that the system over time improves. This was an attempt to get this done by measuring the signals that are available in the visual stream and defining an index that is correlating with the human subjective evaluation of safe driving. Not only that, so when you drive on the road, where do people look at it? So one interesting aspect that we started to notice is the huge amount of text that is available on the roadside. There may be less regulations on what type of text can be there, what type of distractions can be there in terms of advertisements, in terms of signboards, and in terms of many other artifacts that stand on the roadside, which is attracting the attention of the drivers and the passengers. This causes issues in reducing the attention. So when I see a nice advertisement on the roadside, like I look at it, and as a result, I'm losing attention on my driving. So what is required? So and of course, from a different angle, we also found that having such amount of reading and understanding the text is also very important if you ever want to provide driver assistance in local languages with with interesting queries, providing help. The text is a very, very important clue. Not only that, when I drive, like where do I look at it? So since I'm being forced to distract due to many things that are happening around me, starting from the text to other vehicles to the road infrastructures and the potential issues. So it is very, very important. So people are like, there's a lot of distraction and I need to focus heavily. So how do I measure? Where do I look at it? And of course, there has been classical studies with eye trackers and many costly devices, how to do that. So we thought that is it possible, since you have a camera which can have like which mobile phone which has camera on both sides, can we use it to say where the driver is looking? So of course, today's solution is to design the data set to do that. And it's a risky thing because you cannot have a real data and experimentation done on the road with at the risk of driving challenge. So there's an interesting setup which was built in the lab, where people have been asked to focus on certain objects, and then the eye movements and the gaze is captured. In a way, this helps us in looking, since simultaneously you look at the driver and where the driver is looking, and design models that can start predicting in a lab setting. As you can see the picture, the left side is more like a mimicking, it's a lab setting, the vehicle is not really moving. So now we are systematic. So given that we have the first level of model available that can predict where the person is looking, now we would like to see how such a solution can be deployed in the field and online data collection possible without compromising the safety while driving on the road. This is an ongoing effort. So to summarize, looking forward, so we had seen a number of issues in unstructured road conditions and what are the challenges and why it comes and what type of technologies are going to be are important. To say when you look forward, so here are some thoughts on what is really required and what are some of the important directions that we may have to look at it. Indeed, the easy said but very important and maybe all known factors like improved ADAS. Not only that, so there are a lot of other things that you need to monitor on the road. There are vehicle health. How do you use similar technologies for monitoring the vehicle health, and how do we use it in a preventive way before accidents or damages happen to the vehicles, to the road passers, the pedestrians, and also to the damage to the environment? Traffic violations. How do you detect and minimize, or how do you use such things for minimizing the challenges with the traffic violations in a systematic way? We need maps and spatial information which people have access, low-cost map and spatial map infrastructure. So there's a very important part of the infrastructure is the road surface. We had seen some of the initial work on how do you detect quality of road surface. We need to do this at scale, and so that we can build safe infrastructure maps, signs, signals, visibilities, and maintenance. Participatory road safety. Enforcement. How do you enforce such safety, and even education? So in a country like India also has a number of, language barrier. So you need to educate people, and people need to appreciate why this is important, not just for them. People take risk not to create accidents. People are forced to take risk in many situations, and what causes that, and how do you educate so that as a community, as overall, the road safety improves and overall throughput and efficiency of the transportation systems improve. And of course, there are technological needs for two-wheelers and three-wheelers. So Indian roads have a large number of two-wheelers and three-wheelers, and the technology for them requires different flavor. maybe different, some of them may not even require a camera or the visual sensor. And of course, cost and scale are important for the absorption of such technologies at scale by people, by auto manufacturers and many others. And that needs to, such technologies also need to appreciate the language and culture so that we have better human interface and human adaptation is possible. To summarize, so there are dimensions which come from different sides, like data, algorithms and technology, applications and use cases and users. So we need to keep all this in mind and then provide solutions, recommendations, which can work at the level of, say, and give a recommended work with government, vehicle manufacturers, vehicle owners, citizens, startups, academic university, researchers. Everybody has a role in improving the safety. Thank you. So I'll be happy to take.
Thank you so much. Yeah. Very good timing. So we have enough time for some discussions. So any questions from the audience? Hello? So I think as a topic is really interesting, is really inspiring, as you cover many aspects about the autonomous driving in some unstructured rural areas or something. Yeah. So here, my question is, what is the most challenging factor to address in the near future for such like autonomous driving in some unstructured environment?
See, I think that if you look at the autonomous driving, ADAS, and road safety, I think today the immediate challenge is in improving the safety and reduction in death. Zero accident.
Okay, so in this case, in order to reduce the accident,
yes, I think that,
what is the key factor to improve either some kind of like technologies or some like the vehicle control or the infrastructures or some educations, or what is the most important, most effective to address immediately or soon? Yeah.
I think the infrastructure is a very important issue. Infrastructure, education, and if you look at infrastructure is only one part. How do you get the infrastructure feedback? What is required for infrastructure?
Yeah. So, I think you mentioned the data can be captured from different sources with different like the devices. So essentially, we will be having lot of data, yes. And then clearly there is some kind of like issues to fuse or integrate the information from different sources, from different data sets captured from different like devices or sensors. So is that really challenging? Or
I don't think. I think there are a lot of problems to be solved with the cheap sensors today. So what we can capture from some mobile phones or simple visual streams. So there are a number of interesting computer vision problems which are low hanging, which are important to be solved first before we go for costly sensors like LiDAR.
So in this case, can you then comment? Yes. So clearly, yes, we would like to feed essentially everything, yes, into some kind of like a deep learning network or whatever, yes, for some predictions or for some decision makings.
No, I don't.
And then the issue is, do we know exactly what we are doing in order to get what we need?
See, I think I differ a little bit here in terms of it is not all technology problem. You need to understand the rest of the players in the space if you want to solve the problem on the ground.
Yeah.
There's a domain.
Yeah, good. I've got some questions from the audience. The first question is from Adendu. IDD focuses on outside and auto right focuses on inside. Don't you think both inside, outside for better perception and decision making?
Absolutely. Arthendu, like it's a very important point. So we need to look at both outside and inside, and possibly you also need data set which aligns both outside and inside. So IDD, the initial versions of the IDD had mostly outside, I think that some of the new versions of the IDD that come or the new variants of that come there will also have insight. We hope some of them will come soon in this year.
So in this case, I believe it seems the inside, like the understanding analysis, is relatively easier than outside.
Yes. You need to align both. Yes.
Yeah. Okay, another question from Aditya. How do you think an autonomous vehicles would need to tackle the unpredictability of road networks in a rural road environment? Because urban networks do have some kind of predictability associated with them.
Yes, I think the Aditya's question is related to. So if you look at the first part where I mentioned, the prior or the what data should tell us is quite complex when this sort of unstructured does come. Particularly, you raise the issue of city versus like a rural road network. And it is not like there is no prior, there is a complex prior there. So we may need far more amount of data to capture that. That is possibly missing today, because most of the road network data that we may have are straight, wide roads, while these unstructured roads, which do not follow the regulations or the guidelines of good road network, require more data to be captured.
Any other questions from the audience? I think otherwise, I think that's all, yes. I would like to conclude this session with like 2 papers and 1 keynote. Especially the keynote is really interesting and really inspiring. Yes. So hopefully that will really help us to identify the future research and directions. Okay, thank you, Professor Jawahar. Thank you. So let me hand over to Adendu.
Yeah, thank you very much for the nice keynote, and thank you for Young-Whai for chairing the session. So now we are like a kind of a half of the workshop we are done, and then we are moving to the second half of the workshop, and we have a break, I believe, around half an hour. So we are on time. So we should be I'm looking at the timing. Yeah, we are on time. So we'll be back at 3:40 for the second session. It's a long break, so go get some food, drinks, and a bit of stretched. We are sitting here for a long time. Okay, see you all in half an hour time at 3:40 in UK time, and I think your respective local time in half an hour time. Yeah. Hello, Professor Trivedi. Hello. We are just waiting for all to back in 5 minutes time. So we just had a break.
No problem. Good to
Yeah,
see you. Happy
good
New
to
Year
see you.
to
Good to see you. Yeah.
Thank you very much for all your efforts in setting this thing up. Really appreciate it.
Yeah. No, thank you very much for accepting. It is our honor to have you in this workshop. Yeah.
You please enjoy your break. I am right here. I just wanted to let you know.
Yeah, I just grabbed my food. I'm going to have some drink and I'll be back.
Of
soon.
course.
Yeah.
Of course.
Yeah.
Enjoy.
Yeah.
I'll be here. Thank you.
Yeah.
See you later.
See you. Hello and welcome back to the session, to this session. And we will follow the same structure like the previous session. We will start with keynote speech, which is from Professor Mohan Trivedi. And it's my great pleasure to introduce Professor Trivedi, who is an IEEE Life Fellow and currently is a distinguished professor in electrical and computer engineering and founding director of the Computer Vision and Robotics Research Laboratory, as well as Laboratory of Intelligent and Safe Automobiles, which is known as LISA Laboratory. There are many awards the professor has won. I'm just going to pick up few. It is not a there is not enough time to go through everything. He's the winner of the 2015 IEEE ITSS as a lead institution award. And one of the important things is about his team. They pioneered in the area of intelligent vehicles and intelligent transportation systems. And he has won over 20 Best Finalist Paper Award, top 3 of his supervised PhD dissertations, as well as he's a fellow of ICPR and SPI. And he's the a recipient of the IEEE ITS Society highest accolade, Outstanding Research Award in 2013. It is pleasure to have you in this workshop. We are honored to have you. And I'm passing it to Professor Trivedi to talk about his research.
Thank you so much, Professor Behera, and all of my fellow attendees here. It's indeed a great honor and privilege and delight to be here. I was looking forward to meeting you all in Hawaii, but we want to be safe than sorry. So thank you, Professor. Professor Behera, I would like to share my screen. Is that okay?
Yes.
So let's see. Hopefully, we will verify and then go from there.
Yeah.
All right. So. I'm Mohan Trivedi, joining you remotely from University of California. And I hope everybody is doing very well, staying healthy, and it's somewhat of a disappointment that I'm not with you in the room. But I hope that in this suboptimal situation also, we will be able to have a nice, fruitful, and hopefully enjoyable conversation. I do want to thank the organizers, especially Professor Behera and his team from England and some of his colleagues scattered around the world for their kind invitation for me to give this talk. I'm really thankful for their efforts in organizing this and also inviting me. In the next 30 minutes or so, I want to share with you some of the thoughts that I hope would be relevant to the main theme of hazard perception in intelligent vehicles workshop. And to get started, I did set up a little overview of what we can touch upon. So I do want to share with you my own excitement and convey thanks and congratulations to all of you who have been contributing to our field, which has really grown significantly and is becoming an important technological contribution of global proportion. As we do that, I would also share with you some of the things which may not have been resolved completely, but in some sense, given that most of us are academics and researchers here, who like challenges. So I do want to bring out some of the challenges which would allow us to make the intelligent vehicles that we have safer and smoother. Both of those are important terms. Safe is really the most important one. And then lay out certain thoughts which might be, how do we go about making safe autonomous driving? And the key point that hopefully we will be able to emphasize is that really at the heart of making this new technologies safer is something where we will have to understand and predict human behavior. A lot of times when we emphasize autonomous driving, we have a old perception that it is going to be
to really do everything without humans. But as we will keep emphasizing that in order for us to make these safer technologies, we cannot ignore how humans behave and how humans perceive things also. And then share with you some of our own contributions from our little lab. And hopefully we will be able to conclude by saying that this is a journey which is going to keep moving on with everybody's contributions, especially the younger scholars here. And we do want to make sure that as we make our contributions, safety is not forgotten. So I do also want to acknowledge that the work that we have been doing over the decades has really could not have been possible without the generous and continuous support of sponsors, government agencies, state agencies, industrial organizations from all parts of the world, so to say. So that is gratefully acknowledged. And also want to really emphasize that what is being shared with you here is really the things that I personally was fortunate to be a part of a wonderful team of scholars who have devoted some of their finest years in understanding and contributing and teaching me some of the new ideas which allow us to make things safe, intelligent, autonomous driving possible. So before we really get to the somewhat technical discussion, I do want to share with you some observations that I have which relate to the theme of the workshop and hopefully how it, the things that we are talking about in this talk, how they are connected. So the very first thing that I would like to say that I'm excited that the first word in your title is hazard. And I'm hoping that when we say hazard, we are really implying that we want intelligent vehicles to be safe. We also want to appreciate the second term, which is the one about perception. But sometimes just one word perception does not capture the entire computational complexity and hierarchy, which is in some sense embedded in that term. So in my mind, the perception is complex and it goes from sensing, processing, analysis, and understanding at the semantic level of whatever is being sensed by the sensors. So that is something that I will keep in mind. Also, when we are thinking about doing things where hazards are going to be properly mitigated, we want to emphasize that perception is very important, but it is not the thing which will make operation safe. It is also a part of a larger scheme of things, which includes perception, prediction, forecasting, and motion control. And all of them need to really work properly and in some sense holistic manner for safe operation to be assured. So again, we are trying to put some frames around what might be possible in this talk as well as in this workshop and the overall goal of developing safer autonomous vehicles. And one thing that has helped us, and I'm now happy to see that
it's now something which is supported by a larger community of people who are developing and deploying these systems, that emphasis on human-centeredness, system orientation, multiple discipline approaches in engineering, in research, as well as in validation in real world are important before we can really start saying with a lot of confidence that whatever we are developing will be something that will be safe and trustworthy. It is impossible for us to imagine the world without automobiles today, right? And as you can see, that people might say that, oh, it was really in 1880s, 1890s time frame where Carl Benz and people like some of the early pioneers from Japan, in the US, as well as in Europe, who started developing the internal combustion engines and doing prototyping of something which was called horseless carriage. And then it took on. And then certainly during the century, people started saying that this is the machine which changed the world. But in some sense, that is history for us. What you are all doing, and fortunately for us who are in academia and always embedded in the company of bright young scholars, we are in some sense trying to figure out how our current century is going to be changed. And in some sense, we would like to propose that autonomous driving that we are involved in might be crucial in those changes. And in this particular one, I would like to say that let's just look at the early phase of this autonomous driving technology that we might say is really the last 2 decades of last century, 1980 to 2000, where people started developing what I like to call autonomous robotic vehicles. And these were in a handful of academic institutions, really handful of them, and some research labs in industry. But it was something which was making progress, and a few things that you and I now take it for granted, they really came during that particular phase of work. One of the things which we use is the dynamic stability controllers, as well as the adaptive cruise control. Those things, in my mind, really came about when people who were interested in doing some sensor-based controls of vehicles. And the agenda was very big, but I'm just giving some illustrations of things that have come out and they are getting commercially viable and useful, that we don't even think sometimes that they were part or the byproducts of the research during those last 2 decades. Now, I also would like us to recognize that the work that we are doing is obviously interesting, important to us, and in some sense helping resolve major outstanding problems. But there are other people who also help us in make this particular field appropriately fruitful and useful. And some of the enabling technologies which were critical when people were making the early phase autonomous robotic vehicle type of systems were those things where people started building sensors. And the 2 things that I would like to emphasize are those which were radars, so active sensors, and cameras, which were passive sensors, but they came about. And people also were developing onboard real-time compute powers, but this will take like back of the entire van or something like that. The people at CMU and Munich were building, but it was on board and it was real-time. And one of the key things which they were utilizing were real-time image processing hardware also. Now, the phase which I would like to say now the last phase. So this is the early part of this century. There we would say that people really got excited beyond the handful of research labs, but really caught on an imagination of people from commercial domain, from business domain, as well as just popular culture, where people started thinking that we might be, it proved to be closer than what indeed was the case, to development of autonomous vehicles. And I say level 2 because in this audience, everybody would know what I mean by that. But the byproducts of that now we are using without thinking about them as a part of a great novelty, are a whole range of advanced driver assistance systems. And I remember this one because in some sense, since 2000 onwards, our singular focus has been on automotive domain. And these terms we used to argue about, that what should we call our proposal, things related to driver assistance systems and ADAS or driver support systems and things like that. They were not there. The terms were not available, but now this is an established field and people understand what these things mean all over. And that came about in this particular time frame. And already things such as how to lane keep, lane departure, lane change support, emergency braking for collisions that cannot be avoided with a vehicle in front or a pedestrian walking. All of those things are now commercially available in things that you purchase. And in this particular case, the enabling technologies where the red ones focus on it. So everything that was there in the past is carried on, but really in my mind, utilization of LiDARs became quite important and viable. And then this graphics processing units, which was a term that we did not know until in the last phase, but the GPUs became a standard vocabulary, commercially available things where it was not just specialized image processing hardware, but it was really a high compute power, which was available for onboard utilization in pretty harsh conditions. And utilization of something more than just image processing. And all of us know what computer vision is or machine vision is. So machine vision really started playing a role in that. Now let's come to the current phase. And I would like to say that that phase, in some sense, in the last 5 years or so. And in that particular one, what are some of the important characteristics of that? And again, this is a story being currently written, so it is going to be hard for us to really articulate this with full certainty. But I would like to say that here, this whole attraction on fully robotic way of handling development started changing, and we started giving importance to human as an element in this whole ecosystem, where either there are going to be humans who are driving that we cannot model fully, humans who are going to be just jumping in front of us, or humans which are going to be doing things inside the car which are not necessarily something that a robotic system would have accounted for, and things of that nature. But that thing people started realizing we should not ignore. Also at the same time, it started becoming possible that the types of sensors which were developed, and in some sense, all of them, like cameras obviously, but other sensors also, were practical and cost effective for us to generate large amount of real world data. So we wanted to capitalize on that. And this was the thing where if we have got a lot of data, then is it possible that we can bring in addition to machine vision, machine learning, and start really emphasizing safe vehicle operation. And that's something that we are currently exploring and very rapidly making progress. And again, concentrate on things which are in red here. So the enabling technologies in the last 15 years or so, I mean, some of them were there with the GPS and HD maps, but these things became commercially viable and easily implementable, as well as things which were related to machine learning advancements, not necessarily done by people in automotive space, but in broader artificial intelligence related things, which is something that we can capitalize on and start working with. The wonderful thing about human imagination is that we are never satisfied with what is achievable today or in the near future, but we start extrapolating, and we say that if this is possible, can we also get to a stage where we will really look at our vehicles as those things which are going to be safe and smooth, so that the spaces would become for us a moving space going at 70 miles per hour, an extension of our meeting room, our reading room, our relaxation room, or things of that nature. And this is something which is in the back of people's mind, but we are really not there. And sometimes there is always this tussle between what people think we are able to do, and you and I, as people who are engaged in doing things, are aware that, hey, there are some major challenges that we don't know how to solve yet. So I do want us to be aware of those things as we move forward with very specific contributions that people are going to share with us in this workshop. But one thing is also important for us to recognize, that the safety and the dangers, hazards, if I may, related to transportation and automobiles is real. And in some sense, as this particular graph shows from WHO, that it is not, the slope is rising. This is something which also disturbs me. And given that we are a global community, it turns out that the dangers or risks and safety related price which is being paid is unduly, it's not balanced. So it is unduly on the shoulders of what are known as low income or mid income communities. They have much fewer number of vehicles, but much larger fatalities and accident rates than the countries where you and I are sitting here. So we need to be aware of these, because it is quite important that the types of systems that we develop, they are appropriately designed. So when we talk about these data-driven machine learning systems, we will have to make sure that what we are learning and what we are developing is properly contextualized for the environments in which we want to deploy this. All right, so where are we in terms of the technology of self-driving cars? So this is a special issue that IEEE Computer did some time ago, in the last 3-4 years. But interestingly, I mean, again, even though this is a technology magazine, but the artists start giving an idea that many things might be happening where a little vehicle has perfect recognition or awareness of the situations. But at the same time, I also like to utilize some of the things in which people who are really important in development of these technologies. So this is a not even a year-old survey of the people that you see are not technologists, but these are people who run consultancy companies for guiding where the investment should go. And in this particular case, the representation is from European technologists, venture advisors, California-based, as well as China and Asia-based. So this is what they think. So it's not my word that we should go by, which is again technology-centric. But these are the people who know whether things will become viable with the way investments and commitments are made by larger enterprise of people involved in autonomous driving. So they have in this particular report that you can, it's available on the web, but I like the way they divided the major metrics. So there is a thing about technology maturity, so that is something you and I are working on. But then there are issues related to regulations. There are issues related to whether it is cost effective or not. There are things which are related to where will we take things which are going to be not once in a while autonomous, but autonomous in almost all the cases, so level 4 and beyond. And whether we do this thing, would it be accepted by the customers or not? And there is this turning point they talk about, and bottom, you see the 2019 is where they started. And then they are talking about, for each one of those things, there is a time period in which things would be required to happen. And they're really saying, this group is saying that it's another 10 years or so before it becomes, according to these parameters, if we trust them, and again, I have no reason to really second guess this bunch of experts who are not technology pushers, but who are really associated with how technologies are mature, become cost effective, how they are accepted, how regulators look at it and all that. So it's important for us to recognize that it is not something that no matter how many people would say that, oh, we have an autonomous vehicle, but that isn't the case. And even according to that report, they are saying that in 2030, that is 10 years really from now, that they are saying that only about 4 or 5%, one can say, would have level 4 automation. So what you are using currently, what we are using currently is not going to go out of fashion. That we will keep in mind. Other thing that they also give a lot of emphasis on developing is that how much does different types of things cost? And then would it be something that we might be able to do which would be attractive for users to look at it as an option for using level 4 and beyond autonomous driving. And what they are saying that it is really in a very specific application context of robotic taxis. They think that that becomes really cost effective after 10 years, where the prices that are going to be charged for per mile is going to be something which will be affordable to most people. And this is very nice thing that all of us should be aware of, that sometimes in our research labs we can come up with test beds which are going to have a lot of sensing, but when people develop these things, they are really saying that if one looks at the types of things that people are doing currently, which would indicate the precursors to autonomous driving, the additional cost related to technological system augmentation is $70,000. And what they are saying that it will have to go down by a factor of order of magnitude. So below $10,000 in order for this to become cost effective. And they're predicting that it might happen in 10 years, but it's not there yet. Also, one key thing that I would like us to remember, that when we are developing these things, how do we know that we are where we should be in order for us to feel comfortable doing that? So one of the things that people have used in the last 3-4 years, and I like Peter Hancock, a wonderful colleague from Florida, and he's an expert who has devoted his entire career of 40 years looking at human factors issues related to airplanes, and then in the last 10 years or so, more so in vehicles. And really there was this term when people started saying that, oh, it will be ready when it is going to be safer than the humans. Now, this is a provocative title. It came in Scientific American a couple of years ago. But the point is that it's a catchy thing, but really we don't know what is, how safe each and every individual human is. And average human is not what we are hitting for. And even a human who is one that we might be able to customize, they may be safe in one particular moment and unsafe in the other one. So this is a difficult thing to really measure and compare with. And then when we look at that, there are issues which are really related to different parts of the technologies that we develop. So perception obviously is the key focus of this one, but how would we know how good a perception system needs to be to really say this? And then these are really questions to be seen. And this is a book which is going to come out next year by Springer Verlag. But I picked up some of these titles from their individual chapters, and you recognize that there are going to be major issues in figuring out how to validate our perception system, our machine learning systems and all of that. But the good thing is that there are serious researchers like you who are devoting their efforts in developing safer systems. Now, it's also important that if we look at what is available to us today, and when we see perception part of hazard analysis, then it turns out that, and this was, I had given a talk a month or two ago where I used this slide, but this is in 2021, an accident involving a vehicle which was in autonomous mode, and there was a huge collision. It was unfortunately a fatal collision, and the obstacle that you see is not some little child or a pedestrian or a little scooter or a bicyclist, but this is a 18-wheeler that was something that the system could not come up with a controller action to avoid bumping into that. And then everybody, when they see these kind of dramatic hazardous situations and fatal accidents, they start looking at the analysis. I mean, how did it happen, the accident analysis. And it turned out that even at that time, they said that we don't know exact numbers, but there are at least a couple of dozen crashes that are for one particular company that the NHTSA, our regulatory mechanism, is investigating. So these things are not just rare things, they are happening now, and we should address our work so that we don't ignore the implications of safety. This one, I want to bring it up because I think this is in some sense quite directly related to what this conference, this workshop is all about. So this is a cartoon, which is a snapshot of post-accident, post-fatal accident, which happened in my neighboring state of Arizona a couple of years ago, where after the accident, they were required to let go the sensor readings and all. And this is how the system performed at that moment. So what you see there, it says that 1.3 seconds before the collision, the system, the vision system, the perception system there detected the unfortunate bicyclist who was moving across the road. And then it was also showing, this was in autonomous mode, so it shows what was the center of the lane in which it was driving, and then what was the trajectory that it followed, and the distances. So this is at 10 meters from the ego vehicle, 20 meters, 30 meters, and so the person who was there, which was a quote-unquote hazard for the system to properly recognize and mitigate, was approximately 25 meters. So that's not small, short range. But as you can see, that in this particular case, what we don't show here is that the person who is detected there is not just stationary, but that person is also moving, and it moved right in the trajectory of this vehicle. So what it did not have, it had a perception, but it had no forecasting capability. So it could not really figure out what would happen to that trajectory, and will that be something that we'll have to be concerned about or not. So those kinds of things really give rise to a list of questions that scholars like yourself and serious engineers here, we need to worry about if we want to develop the safer, smoother, autonomous driving. And the idea is that we really need to understand the state, preference, intentions, the abilities of humans who are in the vehicle, even though they are engaged in non-driving tasks. We also need to understand the state, intention, the abilities of people who might be in other vehicles which are going around us, as well as there are people who are inside or who are not inside vehicles, but who are bicyclists or people who are just walking around the vehicle, and what are they going to do in a predictive manner. And to do all of that thing, we need to also make sure that everything happens in the time and the accuracies that will allow us to take a fail-safe mitigating operation. So I want to share with you not just some of those defining questions and the basic framework in which we have been working, but also share with you that we are able to make little progress in some of these things with the team of scholars that we have been working with. And one of the key things there is it is really a data-driven, real world-based system. And we don't know all the things that we'll have to use, but in order to really make use of everything that might be going around us and in the vehicle, we have developed this test vehicle a few years ago, which allows us to capture in a synchronized, calibrated, high resolution manner, things which are going in full 360 degrees surround with cameras as well as with other sensors, and what is going on inside the vehicle. And this is a vehicle which has got level 2 as it is sold, but autonomous mode operation for highways and selected environments. So we can use that thing, and once we have it, we can develop some computer vision algorithms. So this is the latest work which came out of our lab with Akshay Rangesh, Dr. Akshay Rangesh now, who devoted 5 years of his effort in developing very accurate 3D detection of vehicles and other objects surrounding vehicle on the road, but utilizing monocular views and some constraints, geometric constraints regarding how vehicles move on the road and all that. And what I want to show you is what I think is a very nice, impressive summary of the types of results he gets with his technique. You can read that paper, it is already published, where he is able to do 3D pose determination and localization in 3D of various objects which are going around it. So it is detection and tracking of multi-objects very accurately as the car is moving with highway speeds of say 65, 70 miles per hour. So this is the type of thing which is possible, and this is really the perception part of it. But as we do that, we also recognize that it's not that we are going to work only on the highways. So we also need to be sensitive and cautious, and we should do our experiments which are going to be involving urban traffic in city streets and all that. And once we go there, we will see pedestrians, we will see bicyclists, we will have different speeds and all that, intersections and all sorts of things which might be happening. And it's not just important to detect variety of object classes accurately, localize them accurately, but also, as you see in this little cartoon here, start coming up with this forecasting where we should be able to see that what would be the safety zone, where I can move with this green arrow is the arrow of the trajectory of the moving vehicle. And we will be looking at multiple candidates when we are doing this, because it's a probabilistic nature. And then given the changing circumstances, the dynamics of the situation, can we come up with the right answer for collision-free driving, which will allow us to do the motion control. Now, I did imply that in order for us to do this work in the latest phase of research, we require very carefully acquired data sets. And many a times when people say it is a data-driven thing, sometimes our temptation to say that all we need is data which is large, huge, but that is not really the case. What we want is appropriately captured data, which is representative of the real world, but also it's something which is going to be curated. So it is not just highly correlated things that we are seeing it for millions of times, but it is really the unique things which represent all sorts of variations which can happen, because that will be very important for us to do if we are going to claim any generalizational abilities as well as things which are related to robustness of our operations. We also need to make sure that there are certain things which are going to come from the sensors, but we need to embed that particular platform into the context in which we are operating. So we need to know where we are geometrically, as well as in some sense the nature of the context which is changing because of the surround, because of the illumination conditions, because of the way things are being driven. And to do that, this is going to be important for us to do this in an appropriately curated data set. So it is not just the size should be large enough, but it should be representing appropriately selected, curated events that can be used in our machine learning algorithms for doing what we want to do. So there is another paper that Ross and others have put together in this workshop, where you will see utilization of this pretty large and what we like to call a unique data set, which we fondly call it lava data set. We are working with Amazon Web Services in this. They're tremendous collaborators here. And we do provide appropriately contextualized large data size, properly curated data samples for people to do annotations on. And so now at the end, I do want to just give you, because I had used that in the title, this idea about transition controls. And sometimes people think that if you are going to do fully autonomous system, why should you worry about controlling or giving the control back to the humans? And hopefully in the early part of this talk, I have said that, I mean, it's not just me, but people who know, they are saying that at least for next 10 years, and in my mind, it really is going to be another 20 years or so before level 4, level 5 commercially available vehicles will be the majority of the vehicles which are on the roads. But until that time, we have to figure out that the system is capable enough to continuously monitor the situational risks of the hazards that it can get into, and then figure out how to mitigate that, either autonomously, so there might be certain braking functions, certain slowing down and parking at a safe place, or there might be things where if they know that there is a intelligent entity like a human who is inside the cockpit, then can we rely on their capabilities to mitigate this particular risk. So we have been, with help of some of our sponsors and collaborators, have been really engaged in what I think is a wonderfully unique, and now it has become very fruitful area of multidisciplinary research, where we are able to look at real world data sets where naturally occurring hazards are perceived, and then appropriate plans are provided in terms of what should be the engagement and when of a human to get out of doing whatever they are doing in a secondary task and take over the control. I will not talk more about it, but I do give you some references to some of this work. It's ongoing work, and everything that you are seeing on the screen is not a cartoon, but it is really systems which are working in selected vehicles at different parts of the world. And now this is again the first slide that you saw at the beginning of this talk, and now I want to bring it back at the end of the talk, where hopefully all the bullets that I'm talking about there, I have made an effort, not necessarily very optimal or not necessarily very detailed, but hopefully you have, I have conveyed to you that there are things which are happening which are very exciting, but at the same time there are for bright young scholars to engage in, to resolve some of the challenges. And really safety should not be an afterthought, but it should be the thought we start out with. And there are great things which we can do, especially over the next 5-10 years or so, utilizing what our colleagues from machine learning and other fields are contributing, and move towards a future where accidents and fatalities and all that would be something of historical nature, but not something that we will have to deal with for our children and posterity. Thank you so much again for the invitation and for your attention. And you have a great workshop and take care of yourself. Thank you. I'm Mohan Trivedi, joining you remotely from the University of California in San Diego. I hope that.
Okay, thank you very much for such an inspiring and very insight into the technological advancement and how it is readiness for the real world scenario. There are a few questions. I'm just going to questions are coming up. Please type your questions in the chat box, which I have already mentioned. And so one of the questions is, are you convinced that the technology will be mature by 2028, and why?
Good observation to some of the things that I presented. That particular year is not something that I am saying. It is one of the relatively recent survey by people who are not technologists, who are not researchers like you and me, or people who are building things, engineers. But these are people who are really observing the entire landscape of technology, regulations, cost effectiveness, user acceptance, and all those kinds of things. And they are saying that until 2030 approximately, only 4% of the vehicles would be in level 4. My observation is this, that whatever is available and whatever is being marketed is woefully inadequate for safe operations in real world. However, unusually as it may sound, people have in my mind overconfidence that what is going to be sold by some beautifully, what I should say, marketed campaign would keep us safe. And that's the reliance on those kinds of statements ends up in tragedies. And these tragedies are obviously, fatalities are bad, but their lives are destroyed, or the families, as well as accidents which happen. And that's quite a bit. And that also creates a trauma. So that's not what I'm saying. But I do believe that it will take 10 to 20 years before I will have a trustworthy vehicle for level 4 operation in overall driving scenarios. But in restricted, segmented applications, like a particular city block in Bangalore or in London or in San Diego, I might rely on a taxi, which is fully automated in level 4 in 5 to 10 years.
Thank you. Another question is giving the control back to the driver in case of emergency. How do you make sure that the driver is ready, and how the companies should tackle this situation?
Beautiful, beautiful. Yes. So that is precisely what we are working on in our group, is that we really need to make sure that what people used to call driver monitoring, and initially for the first decade or so, the emphasis was really on making sure that they are engaged in driving. And in last 5 or 10 years, really in 5 years, specifically, I have been emphasizing that we want to make sure that drivers can perform non-driving tasks safely. So driving is going to be required to be engaged in driving as a primary task. We want humans to do in a rare situations, but very risky situations. So most of the times the car should be able to say that, oh, my dear human is having a nice little nap, or he is having a nice lunch break, or he is having a nice game of tic-tac-toe, or whatever that is going on. but it knows simultaneously that what is the safety margin in which this fast-moving mobile platform is currently embedded. And when it figures out that over the next 10 seconds or 20 seconds or something, it's going to have an extremely high confidence that unless something else is done, we are going to get into the red alert of point of no return. Then it needs to figure out that if this guy is sleeping, there is no way I can engage him or her to take over the control. But now I need to figure out the emergency maneuver. So I will get into the emergency lane, or I will do something safely on my own. I'm talking about the vehicle cognition is thinking like that. But if it also figures out that, oh, he's just playing the game, and if I give the right alert, then he can just take a look at what is going on in the situation and appropriately mitigate out of that. And that is what we like to call an observation readiness index, that we need to be continuously monitoring that how ready the person, intelligent entity, and I don't want to call that driver, because most of the time, 99.9% of the time, they are not driving. The vehicle is driving, the robotic system is driving. But in that small time that it is needed to take over, are they ready or not, and how ready? And then based upon that, we figure out what should be the mitigation mechanism. Nice thing about it is that we started a serious project with the help of some of our collaborators 5 years ago, have conducted experiments with hundreds of real world subjects in situations which are very well designed by human factors people on old airport where they can create a variety of situations and require these drivers to do operation in autonomous mode and presented them some kinds of these emergency situations and developed huge data set and then figured out, can we learn how to mitigate that? That work has already moved into a pre-development stage with one of our sponsors. I have a feeling that we have been writing about it, so you can find some of those papers. But I do believe that in next 5 years or so, there would be things which are based upon giving a very reliable alert and advice to the drivers in taking over the control.
Okay, thank you very much. And I think that is the end of this keynote speech. And thank you, Professor, very much. It's a very nice and inspiring talk. We'll move to the next talk. The next, just to let you know that the next two talks, again, the invited talks, and the first one will be from Rohan Chandra. Rohan, could you please start preparing your presentation? While you are preparing, I'm just going to tell briefly about Rohan. Rohan is a fourth-year PhD student at University of Maryland, and he is researching on developing new algorithms and systems to perceive, predict, and plan among human drivers in dense, heterogeneous, and unstructured surrounding. And I'm going to hand over to you, Rohan. Thank you.
Thank you, Ardindu, and thanks for the wonderful introduction, and thank you for having me here. So hi, I am Rohan, and I'm a final year PhD candidate at the University of Maryland. I work with Dinesh Manocha. The structure of my talk, the title is Autonomous Driving in Unstructured Traffic Environments. The outline of my talk is roughly divided into 3 parts, and hopefully each part should take about 5 minutes, and I'm going to leave the final 5 minutes for question and answers. So just going to start the timer here so that I'm on track. Okay. And throughout this talk, I'm just going to speak for continuous 15 to 18 minutes, and I'm going to take questions at the end so that I can get through all that I need to get through in one go. Okay, so most of us already are aware of what unstructured traffic environments, unstructured driving scenarios are. So I'm probably going to speed through this first part of introduction. But just to give you a sense of what an unstructured is, let's go back, take a step back and take a look at what a structured environment is. So in this video, I'm showing you a video of a Tesla Autopilot, one of the most recent versions, which is driving in downtown Michigan in the United States. And as we can see, the Tesla is doing a pretty good job of driving by itself. It's changing lanes, it's navigating intersections, it's coordinating well with the agents around it, and its life is good, right? But what I want you to focus on here is not the driving of the car itself, rather the environment of the car in which it is driving. And more specifically, what I want you to focus on is the well-marked lanes, the smoothness of the roads, the sparsity of the traffic environments, and most importantly, notice how well behaved every agent is, right? So this is an environment which we call a structured environment, a simple, structured, and sparse environment, right? And now in another video, in the next video, what I'm going to show is the exact same environment. This is actually a video that is like an extension of the previous video. The same vehicle is going to navigate in this environment, but with one minor plot twist. So take a look.
So we've encountered this before. We have somebody kind of sticking out from the left turn lane, and the car needs to just go around them, and it's just stopping instead. The person, oh, okay, I need to take over here because there are people behind me, and that was not very good. We're going to report that. That's strange.
So what happened here is that the same Tesla vehicle that I showed you in the previous video is driving along its road, but there's a truck that's sort of like jutting out of its lane into the path of the autonomous vehicle. And it's not like completely in the path of the Tesla. It's like a slight percentage, a small portion of the truck that's sort of like spilling onto the lane of the Tesla. But the key point that I want to drive home here is that given a perfect world, all it takes to mess up the Tesla, all it takes to make it fail is one small part of a car, of a vehicle that's sort of like over the lane marking. That is it. That's such a tiny irregularity causes the Tesla to fail. And this is one of the most recent versions of the Tesla. So I'm not bashing on Teslas over here. Don't get me wrong. I'm not a critic of Tesla. But what I'm trying to make a point here is convey the message here is that environment matters. And if a slight irregularity is able to impede the proper functioning, the safety of the autonomous vehicles, then what chance do autonomous vehicles stand in this environment? Now, this is what we refer to as an unstructured environment. And before we can start addressing the question of how autonomous vehicles can begin to drive an unstructured traffic like this, we need to first define what an unstructured traffic environment is. Unstructured traffic environments are characterized by three broad factors. The first factor is the traffic density. Notice that the traffic density here is about 10 to 15 times higher than what current autonomous driving is used to. The next factor is heterogeneity. Heterogeneity is measured in terms of number of unique agents per frame. In this video, we can see there are auto rickshaws, bikes, you can see a cow going by on the right, there are pedestrians, electric vehicles, and so on. So there are lots of agents, about 9 or 10 unique agents per scene, per frame at any instant of time. That is what I refer to, or what we refer to as heterogeneity. The final factor is the unpredictability of the drivers, and this is the most crucial factor. Contrast the driving here with the driving I showed you in the previous video. All the drivers in the previous video were well behaved, following all the rules, and there's a general structure to it. Here, the only rule here is that there are no rules. That is the law of the land. Everyone is breaking traffic rules. Everyone is not following lane driving. They're not following the same lane. They're driving on the wrong side. They're ignoring traffic lights. This increases the unpredictability. And these three factors combined results in an unstructured traffic environment. Now, why is this a problem? Why do we want to focus on unstructured traffic environments? The reason is that, we already have a momentum going for structured traffic environments in regions like the US, Europe. We already have we have the recipe. We know what the ingredients are to reach, autonomous driving. As Professor Trivedi mentioned in his talk, 10 years, 15 years, 20 years, it'll take time, but we have an idea in our head as to how to proceed forwards. In unstructured traffic environments, we have nothing so far. We don't know where to even begin. And so my dissertation research, or my PhD research, proposes new techniques, new algorithms for autonomous driving in dense, heterogeneous, and unstructured traffic surroundings. So there's a typo, and this should be a driving. Okay, so that is what my research, my PhD research is about. My contributions are throughout my PhD has been across the entire autonomous driving stack. There are three fundamental tasks, and this is also something what Professor Trivedi mentioned. You have perception, which is all about making sense through cameras, LiDARs, radars, and so on, using machine learning, machine vision. Once you gather all the data from the perception side, you plug it into prediction, and in prediction, you typically perform, you can either forecast the trajectories, you forecast the intentions of drivers, and after prediction, you get planning. Planning is about, control, it's planning, it's decision making. Once you get all the information, how should each agent decide to move? That is planning. Now, I'm going to diverge a little bit from this well-established pipeline and assert that there is another component, another module that is essential, especially for unstructured traffic environments, which is driver behavior modeling. Now, driver behavior modeling, which I'm going to get to in the next part of my talk, is all about how to, observe drivers and determine the personality of the driver. How is he driving? His style. Is he aggressive? Is he conservative? Is he shy? Is he crazy? And so on. And this sits somewhere between prediction and planning, because the output of behaviors, when you figure out how a driver is driving, how can you use that for planning, right? So it sits somewhere right before planning. So that brings me to the next part of my talk, which is driver behavior modeling, what it is, why we need it, and how we do it. Okay, so we in my PhD, I've worked with Dinesh, I worked with an advisor on driver behavior modeling. We published a series of 3 papers. 2 of them have been published in robotics conferences, and the third one has been published in a autonomous driving journal. So come back to why we need driver behavior modeling. If you look at most of the accidents that occur in autonomous driving, it's when it involves multiple vehicles. Most of those accidents occur because human drivers are notoriously bad at reacting at the very last minute. We want to know ahead of time that if a crazy driver is trying to aggressively cut in front of us, we want to know that ahead of time. If there's a driver, who's trying to tailgate us and, driving right behind us, we want to know that, because if we, brake suddenly, the guy behind us is going to run right into us. So we want to know what other drivers are going to do. And this is especially crucial and necessary in unstructured driving environments, right? So now driver behavior modeling is really, really intricately complicated and hard to define. There is no clear definition of a driver behavior. It is subjective, it is rooted in psychology. But what we can do is we can characterize driver behavior into 2 broad categories, aggressive and conservative. And each category is characterized by a fixed set of maneuvers. So intuitively, semantically, we know that aggressive driving is characterized by overspeeding, overtaking, sudden lane changing, and so on. Conservative driving can be characterized by uniform speed, like well-behaved driving, conforming to a single lane. And it sometimes also includes shy and timid drivers who may respond to pressure from other drivers. So this is like the broad taxonomy of driver behavior that is accepted in human factors and traffic psychology, and so on. This is what we use in our approach to model drivers as aggressive or conservative. Okay, so now comes the question of how do we model drivers as aggressive or conservative, right? And the answer is simple. It actually comes, the intuition for how we do it comes from my experience of driving in India. Indian drivers do this intuitively. We look at a driver, we can intuitively figure out whether the driver is aggressive, conservative, is going to break the rules, is he going to let me pass, and so on. And I sat down and I introspected further as to what is the scientific reason, what is the psychological hook that we were able to, Indian drivers are able to do this. And it comes to a notion of relative behavior. And an example of relative behavior as follows. Say a vehicle is driving at about 65 miles per hour. And now I put the question to you, is that driver aggressive or is it conservative, right? And the answer depends. We cannot say right now. We cannot just be going off on this information of 65 miles per hour. We don't know whether he is aggressive or conservative. He could be aggressive if he was driving in downtown, but he could be conservative or even just neutral if he was driving on highway. Similarly, let's say another example, a vehicle is changing lanes 3 times per minute. Again, the question is that vehicle aggressive or conservative? We don't know without more information. It's aggressive for a truck just because of the size of the truck, the low maneuverability of the truck. It could be neutral for a car. Again, it could depend on traffic density. It could be aggressive if the vehicle was frequently lane changing in heavy congested traffic. It could be neutral or conservative if he was lane changing on a sparse highway. Pretty odd to do that, but not aggressive. So relative behavior is the key. And that is what we use to model driver behavior. And I'll show you why using this relative behavior is advantageous. What benefits does this give us over machine learning methods that they take in a whole bunch of things as input, like the video, the images, the trajectories, the HD maps, and then try to figure out behavior from that. I'll try to contrast it as well from those approaches. So our contribution, in our approach, in our research, we present a real-time and general metric called the C metric for characterizing driver behavior based only on the positions of vehicles. And this is very, very attractive when we're not relying on other things, just on the positions. It makes our approach very simple and real-time. We also propose a new evaluation protocol called the time deviation error to evaluate driver behavior recognition methods. Now, this is especially important because when driver behavior modeling is something that is still not very mainstream. It's still it's a sort of relatively new area of research. So there aren't many good protocols or metrics to sort of assess how good your model is. So we propose a new metric to measure our metric, so to speak. Now, why does relative behavior, how does our behavior model differ from existing approaches that either rely on inverse reinforcement learning, or they rely on, let's say, supervised learning or other kinds of statistical approaches? Well, for one, there is no data processing required. We don't need to clean the raw data that we get from LiDARs and cameras. And that's a huge thing, because we can then turn our approach into a plug-and-play system integration. And we just say, you give us the raw positions coming from the cameras and depth cameras and LiDARs, we'll give you back a behavior number. No large neural networks involved. The attraction here is that we don't need to rely on all the large autonomous driving data sets. We don't need to rely on collection and the cleaning and all the effort that is involved. No large neural networks means no memory footprints, no any negative connotations that come with neural networks. As I mentioned before, only trajectories are required as input, which makes our approach sort of simple, and it makes it real time. So these are sort of the benefits that comes with our method. Now, how do we model this relative behavior mathematically? In the interest of time, I'll just put this out there. The ideas are in the paper. I'm happy to take this up afterwards, after the talk as well. So we use this notion of vertex centrality. And vertex centrality is a concept in graph theory, which measures the importance of a vertex with respect to its neighbors. So we use these two ideas of degree and closeness centrality. The degree centrality measures longitudinal behaviors. These are behaviors that are along the axis of the road. So this measures, behaviors like the overspeeding, slowing down, and so on. The closeness centrality measures how central a vertex is in a graph. And this is used to measure the lateral behaviors of a vehicle, which is perpendicular to the axis of the road. So this measures things like, your lane changing, your overtaking, cut-ins, and so on. So a combination of these two centrality functions gives you the behavior. I'll go through the approach very quickly. The input consists of the trajectories of all the vehicles. This is, the trajectories consist of the positions in meters. That's the first step. The second step consists of the forming traffic graphs of the traffic at every time step. And once we get these graphs, we can get the adjacency matrices, the Laplacian matrices, and so on. And the final step is we use the vertex centrality functions and we apply them on the graphs and we compute a behavior metric. This is sort of like the high level approach. There are some technical nuances that are in the paper. I'll quickly go over the metric that we use to measure our work. So this is called the time deviation error. It measures the temporal gap between the timestamp when a human identifies an aggressive behavior and when our symmetric algorithm identifies that exact same behavior. And if you notice, this metric or this protocol is not evaluating the accuracy of our approach, because by design, because it's a deterministic algorithm, it is always going to be near 100%. So what we are measuring through this protocol, evaluation protocol, is a precision. We want our systems to be precise. The moments at which a human driver recognizes a driving behavior, we want our systems, our machines, our computers to be able to identify that behavior at the exact same time, right? And that is what this metric is doing. So it measures the temporal gap between a human identification and our algorithm identification. So here is here's one result where we analyze the behavior of drivers across regions across the world. We compare in Singapore, USA, China, and India. And we take these trajectories, which are in the first three columns. In the final column, we plot the centrality curve. And essentially what we're trying to show is that the distance between the two vertical dashed lines, the orange line and the blue line, that represents the temporal gap. So we want the distance between these two lines to be small, right? And what we're able to do is we're able to show that in all of these regions, we're able to take their trajectories and compute the behavior of all the drivers. So we can show, we can predict whether drivers are overspeeding, overtaking, and we assign a real valued number to those behaviors. So let me just jump to the next part. So future work. Autonomous driving research, as Professor Trivedi mentioned, is data-driven in nature. There have been a lot of autonomous driving data sets in order to advance autonomous driving research. However, most of these data sets cater to structured scenarios, the ones that I showed you in the beginning. We need a data set that is that caters specifically to unstructured traffic scenarios. There have been efforts in this area with the IDD data set, that is one, which is also mentioned in this table. Our group has released a brand new data set called the Meteor data set. And what sets this data set apart from all the other data sets? We can debate on, the inclusion of bad weather, driving in daytime, nighttime, road type, and all of those things. And those are good to have. But what sets our data set apart is the inclusion or the containment of rare instances. What do I mean by rare instances? Well, let me show you. So we show you, we have instances that that contain, we have marked and provide annotations and labels for people or folks that are overspeeding. We have instances for, crazy maneuvers like zigzags. In addition to keeping all of the elements of unstructured driving like density, unstructuredness, rule breaking, and so on, we have drivers who are, performing these kinds of maneuvers which are not captured in any other data set. So let me just let this video play out and you can see for yourself. So this data set was captured in India, and all of the traits, the styles, the characteristics that make Indian traffic, Indian driving so unique, that is what we have captured in this data set. We have labeled actions, we have labeled scenes, time of the day, weather, kind of the driving scenario, whether it's highway driving or rural driving. And if you want a snapshot of all the characteristics that are contained in this data set, this is like a mind map that consists of all the features, characteristics. As you can see, these are all the things that are labeled. So we have density, road type, conditions, agents, all of these different types of agents, the data type, behavior, 17 different types of behaviors, in which includes rule breaking and so on. So the best thing about this data set is that it breaks most of the perception that we take for granted, that we take state of the art. The first four columns, the first four rows describe the perception, object detection perception results on the state of the art data sets. And we have pretty decent results. Object perception breaks on our data set. As you can see, these are poor results. And what the conclusion in this slide is that what perception that we're taking for granted right now, there's still a lot of room for improvement for unstructured scenarios. And this result is sort of meant to convey the urgency or to convey the need for more efforts and perception for unstructured traffic scenarios. So I'm well over my time, so I'll just conclude quickly by saying that we motivated autonomous driving in unstructured environments, but for this crowd, I don't really need to do that. We all know why that is necessary. But most importantly, I presented a new way for modeling driver behavior for human agents. And in future work, I presented our new efforts for pushing out this new data set that we've collected for Indian traffic scenarios, which captures all the unique elements that makes Indian driving so unique. And thank you for having me, Ardintu, and to the rest of the organizers for this workshop. I can be reached on this email and I can take questions now.
Thank you, Rohan. Thank you very much for a nice talk and the nice presentations of the materials, data sets. That's nice. I'm just waiting if anybody is typing questions. Meanwhile, I'll ask a question to you. You mentioned about that your method is based on trajectories, isn't it? And then how sure are you that trajectory computed by existing whatever object detector tracker is error-free? How much noise your model can tolerate in that detections or trajectory predictions stuff?
Right. So what we observed in our experiments is that our model, because our model is based on the notion of relative behavior, right? Or so it uses, the distances between the absolute positions. So even if, our model can tolerate a lot of noise, we don't need to do a lot of processing. We stress test our approach and, introduced, artificial noise ourselves by blurring out, the positions of agents by adding Gaussian noise. And, at the very extreme, at the extreme of breaking our system, we can easily apply regularization techniques like the Tikhonov regularization, and we reduce the condition number of the linear algebraic system that ways, and then we can take care of the noise that ways. But on the whole, on its own, our system can automatically tolerate noise. As in that we were able to work with the ngsim dataset. If you've heard of the ngsim dataset is full of noise. It's like very, very noisy dataset, and typically whenever you want to work with the ngsim, you have to take into account the noise in that data. But our system worked with the ngsim dataset out of the box. We worked with the Waymo, the Argoverse dataset. We worked with a dataset that was collected in Singapore, and all of those datasets, we just extracted the positions from the dataset, and we didn't need to perform any regularization on it. It was only when we wanted to stress test our system and push it to the brink of failure that we found that, okay, let's do some regularization, and minor, very off the shelf, we take L1 regularization, and we can even smoothen out, we can reduce the condition number under those circumstances. So we can show that our system, we have actually performed follow-up research on this, and we integrated this driver behavior modeling with planning approaches, with the reinforcement learning, or we can do control-based planning, optimization-based planning, and it actually fits very, very well with downstream tasks like optimization-based planners and reinforcement learning-based planners.
Okay, so, thank you. I think that's the same questions asked by Professor Liu as well. This is my last questions. Now, you mentioned about that unstructured environments. If you think about an unstructured environment, you saw some the traffic scenario in India. It mostly depend on the driver or road infrastructures, or the lack of proper infrastructure, as well as the lack of education to the people. Where now the previous keynote, Professor Jawahar talking about it, we need to look into infrastructure and education. So let's say in 10 years time, people will be more educated, the structure will be improved at the developing nations. Then how do you see that unstructured become going to more structured scenario? Like in Western countries, we see that road scenario and traffic situations. So how do you see that kind of changes as India move forward? The technology will impact on such scenarios.
Right. The good thing about the efforts that are going on right now in structured scenarios, especially in developed nations like USA or Europe, most of those autonomous driving systems, they're based on rules. Like they require lane markings. As I showed you in the Tesla video, you take away a part of the lane markings and the Tesla fails, right? So it is based on rules, and it's based on the structure. It requires the structure, especially for example, when you're navigating an intersection, right? It requires the right of way rules, right? It requires knowledge of who goes first. That's how the Teslas are sort of, not Tesla, I'm just going to general autonomous vehicles. Okay. They're more, conservative and shy in nature. They let drivers pass. But more than that, they require, knowledge of the structure and the rules. So the kind of things that we have right now in developed nations, some of those elements, or some of that technology can be translated to or integrated with the efforts that we're trying to make for unstructured driving. So what I feel is that, in my opinion, we need new ideas, new algorithms, and new research for unstructured driving. And then as we take that forward and we get more education and more awareness for unstructured drivings. Once we have get some of that coming in, we can pull some of the efforts or some of the advances that we already have right now for structured driving, and we can sort of integrate the two. So we have good engineering advances, good engineering that's happening right now, but we need to couple that and integrate that with good algorithmic innovations for unstructured driving. So a little bit of integration between the two would be required in the future.
Okay, thank you very much. Thank you very much, Rohan. Yeah. Okay, we are going to move into the next presentation, which is another invited talk from Dr. Ashish Bera, and who is a assistant professor at the Department of Computer Science and Engineering, SRM University. And prior to this, he was a postdoc in Agile University, UK. And his research focuses on AI, computer vision, and deep learning. And he's going to talk about the driver activity monitoring, I believe. Yeah, it's over to you, Ashish.
So thank you, sir, for this opportunity to be a part of WACV and in this. So am I audible to you?
Yeah, it's clear.
Yeah. So I think my slides are also visible.
Yes.
Yes. Okay. Thank you. So hello everyone. So my topic of today's talk is key point based deep attentional network for driver distraction recognitions. So most of the previous speakers have been discussed about the road scenario, traffic conditions outside the vehicle, but our work is mainly based on the inside activity of the driver for the autonomous vehicle systems, which causes sometimes the distractions of the driver, so that it can avoid the different accidents or hazards. So at the right side, you can find that some of the recent statistics about how this in-vehicle inattention of the driver can cause the distraction and how it will affect the accidents. So like in case of, according to World Road Statistics in 2001, the total number of accidents, so US is the first, then Japan and India third, and UK is 13. And also, if we look into the modern handheld device like mobile phones, so in Great Britain, around 1% per drivers are involved while using this smartphone while they are driving. So therefore, our work that is based on this driver activity recognition is very important and challenging task for intelligent vehicle to monitor the secondary in-vehicle activity of the driver, like talking to the phone, or drinking, or reaching behind, and so that it could distract the driver and avoid the different accidents. So before this deep learning area, the key point based method like the SIFT or the SARP has better performance for the feature learning using the engineering or handcrafted features. And after the deep learning, it has been shown that those important features can be learned automatically by the network itself. So our objective is to combine the benefits of these two methods so that we can use or enhance the performance of the system for mainly for the image recognition of the fine-grained discrimination, like subtle variations during whether the same person is driving, but he may be involved in the mobile phone, texting left side or right side, or drinking. So it is a very challenging task. And not only this network or approach is valid for driver activity, it can be also used for the wide range of human activities and fine-grained image recognition. So to achieve this, firstly, we have developed an attention-based deep network model where our objective is to learn the local and global contextual information from smaller patch to larger patches and to the whole image. That means for a given input image where the person is say driving safely, a person is given, then we have applied those key points like the SIFT, which detects what are the key locations of this image spans around the overall the image. So this SIFT, we know that is detects the key points as well as the locations of those different distinguishable or distinct regions. Also, this SIFT is invariant to affine transformation, scaling, rotation, etc. So first of all, we apply these shift key points to localize the different informative regions over the image. Then we have applied a Gaussian mixture model to cluster those different regions into smaller regions, into different regions. And then we surrounded by those each regions in a as a bounding box, so that this creates some different regions ROIs with different dimension and multiple scales of, so these sizes are different. So these we called as a primary regions. Now, in addition with these semantic regions, we have also combined each of these primary regions to make a larger patches, one-to-one combination of different larger patches. In that case, the regions may span over a different region from far apart, but those are very informative or useful to discriminate the different actions happening inside the image. Finally, these different regions, semantic regions, along with the full image is passed to our deep attentional network. So here we emphasize the importance of different regions of this semantic regions and which region is important to make the final decision to classify that image or whether the driver is attentive or inattentive. So after classification, it will assign the corresponding class probability for safe driving the highest in this case. And to implement our network, we have used the ResNet 50 as a backbone, and our attention module is built on intra-attention, that is self-attention, as well as the inter-attention to find out the which region having much more importance compared to the other regions. And the intuition behind generating the semantic region, if you see that from this particular input image here, a person is driving. But if we use those only one region marked with red color or green color, those are called primary. It captures partial information about the driver. Either she is drinking or she is driving. So therefore, we combine these two regions to make a larger patch, which defines that the person is basically drinking while she is driving. So basically, the driver is inattentive. So in this case, the autonomous or the intelligent system should take over and go for the autonomous driving state to avoid any accident or any hazards. So therefore, if we have k primary regions using clusters of using the GMM, we can generate another k into k minus 1/2. So altogether we can have k plus k into k minus 2 different total regions. So initially we considered 8 primary regions, and total combining 28 secondary regions, we get 36 regions, which gives the best performance in our attentional deep model. And we have also verified that how this region is important or how this is synchronous with the class activation map, which has been shown at the right side. So here we can see that the class activation map, which is shown in the yellow and the red color, is also synchronized with our this region, semantic region proposal algorithm using these key points. And this is our overall architecture of the model, where we have used the backbone in as a ResNet 50, and the convolution features of the last layer of the block 5 has been taken out, and then we have applied the self-attention. Now the self-attention is inspired from the attention mechanism of the natural language processing, which is now a de facto for all the computer vision problem. And then we have also generated those semantic regions by combining and applied a squeeze and excitation network, which has been shown at the right side using a residual connection. So this residual path gives a smoother gradient flow of the learning process, which enhances the learning. As well as our attention mechanism is adapted from the self-attention gun, which is very useful for learning the long-range dependencies between the different regions, which may be far apart from one to another location of that image. So, and then our attention module is combination of the intra-attention, that is the self-attention, as well as the weighted attention, that means how much one region is important, emphasizing or considering all other regions to get the attentional importance of the different regions. And in the classification module, finally, we have applied the global average pooling and the global max pooling to get the final important features and finally fed into the softmax classifier. So this is the overall architecture of our AG network deep architecture. Now we have tested our model in different diverse set of different data sets, including the driver activity like AUC, V1, V2, normal day life actions like the Stanford 40, and generic image classification like Caltech 256, as well as fine grained food 101. And we have shown that different backbone networks and our method outperforms all the previous best approaches on these different data sets. And also our model complexity for the whole model is also very reasonable, lies within 54.8 million with an inference time is 5.2 milliseconds. And the usefulness of every component of our network is also tested, like from the baseline model, the maximum jump we have received or gain we can get using our semantic region generation algorithm, as well as our attention module finally again boost up the performance from 90 to 94%. Compared to other region generating algorithms such as mask CNN or CNN feature algorithm, our method is completely outperforms those available region detectors. According to using this model, we have also generate or applied to recognize the driver distraction state for the driving. So in this case, so here in the AUC V2, the data set what we have considered, it is a basically fine grained data set. So here 10 different human activities are there. Out of 1 is only the safe driving, and rest 9 are the distraction. That means the secondary activity, either the driver is involved in other activity. So here we address this problem into a binary classification problem, whether the driver is normal driving, attentive, or cause any distracted activity. According to this previous network what I have just mentioned before, we have classified into 2 states, driver safe driving and distraction. So if the driver is distracted, then the autonomic control will pass and a collision avoidance algorithm will impose for the safety by braking automatically, such that, so this part is collaborated work with the IIT Madras, where in their engineering department design lab they have applied this collision detection algorithm using a hardware in the loop architecture. So what we have done for this purpose, now in case of previous speakers have shown the data sets involved in the outside driver activity, but inside the vehicle there is very unavailable for public data set which will involve different driver distraction causes. So therefore, using this AUC V2, which is basically a image recognition data set, we have simulated in a realistic manner for a longer sequence, say around for 1 minute of video, which will show whether the driver is attentive or distraction. So for this purpose, for a video clipping of around 1 minute, we have started a video where the driver starts a normal driving and then involved in some secondary activities like talking over the phone. So, and then again he drives normally. So here you can see that the ground truth levels are using a green color and predicted level is using red color. So here when our model detects there is a distraction, so the autonomic braking system will cause and the driver the system will stop to make a maintain a safer distance of 10 meters. So using this model, using transfer learning techniques, that means we have trained our model using this driver activity recognition of AUC V2 and directly transfer learning with another driver dataset DMD, which is recently published. Part of this dataset is available but not fully available. So we have trained our model in this first dataset and recognize whether this driver is doing attentive or not attentive. So in that case, we are achieving around 98.7% accuracy for safe driving state, and distracted driving state is around 98.8%. So these are the different time span where the driver is involved in either safe driving or distracted. Now here we have shown the video what we have done. So here we have basically tested two situations where the lead vehicle is at standstill and this is the host vehicle. So once this automatic braking system finds the driver is distracted, it presses the brake and make a safer distance of 10 meter. So for this case example, say the DTS goes high, that means the driver is inattentive around 16.5 seconds, then it presses the automatic braking system so that the accelerator would decelerate and the threat is detected by the collision avoidance algorithms around 19 seconds so that it maintains a safer distance of 10 meters to avoid that hazards. So this is our approach to how to handle the driver monitoring while the driver is distracted for a collision avoidance algorithm. Now, for this one, now most of the driver activity recognition works on based on the either still images or in laboratory setup, because this is a very difficult to capture the video in real life situation for detecting those accidents or secondary activities. So not enough public video dataset is yet available for driver recognition state. So therefore, we need to generate or create another new data sets for in-vehicle secondary activity monitoring, as well as we can consider very complex road scenarios like the IDT, what the other speakers have been shown, that for high traffic density, lane changing maneuver, lighting conditions, road curvature, so environmental conditions. So those are the open challenges still that can be addressed to be solved in near future. Also, here only we have considered the binary classification, whether the driver is attentive or distracted. So we can also emphasize further or fine classification whether what is the level of the distraction of the driver is caused, because the distraction level is also important to take over the request for autonomous vehicle and avoid the hazards. So these are the open challenges that can be solved by by near future. So this can be used for the further safety of the vehicle passenger for the intelligence systems. So these works are supported by the UKRI and British Council and Government of India under the CHARM project. And I would like to thank these collaborators for their sponsorship for this HPIV workshop as well as the CHARM project grant. These are the references and our publications in IEEE transactions and 24th ITSC conferences. And thank you for this opportunity, and any question?
Thank you very much, Ashish, for presenting the work. And yeah, we have a few questions. Just one question is coming from Young Wai, that shift key points are supposed to correspond to the driver's parts and potential distracting and interacting object. How robust are these key points to imaging noise and other objects?
Now, shift key points are basically used as a mainly for feature descriptor, which are having some advantages like that, invariant for the translation, scaling, which are also available for the deep learning features. But these key points are also capture the noise information. But in realistic situation, we may also have some noise in our video generation. So I think in addition with the deep learning feature learning as well as the shift both can be combined, and it can enhance obviously the performance.
Okay, thank you. What kind of the model? Just to ask you that, no, you use the shift features and then to generate the bounding boxes, but there are other existing technique for the object proposals. For example, in object detection, so there is a proposals, bounding box proposals. So how do you think that your key point based bounding box is different to those object proposals?
Yes, to find out those edge boxes, mask RCNN, and the feature clustering during the runtime in the CNN feature clustering. So we have also tested that the mask RCNN can generate thousands of region proposals, including the redundant information. So from those large number of bounding box to get the lesser number of or the most important regions is quite time consuming as well. So we have tested with this max RCNN based approach, and where the accuracy what we have obtained around 7% using max RCNN, while our approach gives around 95% accuracy. So I think our approach is better than the max RCNN based object detector and other clustering approach which are available.
Okay, thank you very much. Okay, that's the now we are moving into the paper presentations. But before that, just to let you know that we are aware of the time. People might be concerned that we are late. Yes, we are aware of the time. At the moment, we'll give you 5 minutes break just to stretch and take a glass of drink or tea or coffee, and then we'll be back in 5 minutes. Because in the next season there are 3 papers supposed to be presented, only 2 persons is presenting, so we'll be fine. We'll be finishing in the time, so no worry about the timing of the presentation at the moment. See you in 5 minutes.
Thank you, sir.
Hello and welcome back. I think it was a quick, short break. I'm going to pass over to my colleague Yonghwai Liu to chair this session.
Hello, everyone. Good morning, good afternoon, good evening. This is the last, but of course not the least session of this workshop. It again includes unanimous 3 papers from the submissions from the others and 1 keynote. Okay, so the first paper is entitled On Salient-Sensitive Sign Classification in Autonomous Vehicle Path Planning, Experimental Explorations with a Novel Dataset. The talk will be presented by Ross Greer. Okay, thank you. Over to Ross.
Great, thank you very much. And I'm going to go ahead and share our video presentation now.
Yes, please, yeah.
My name is Ross Greer, and I'm presenting on salient-sensitive sign classification in autonomous vehicle path planning, experimental explorations with a novel dataset. We define a sign to be salient if the visible sign provides an instruction intended for the ego vehicle location before the next decision point, independent of the actions of other agents and instructions provided to other lanes. First off, we have a complex traffic scene shown in this montage, and there are many signs detected. The question we seek to answer with the property of sign salience is which signs help you from the position of this vehicle to safely navigate the complex intersection. Similarly, we can ask, are all detections equally important? In this scene, there's a stop sign, which is for the imminent stop for the lane that we are in, and there's also a speed limit sign for the cross traffic. And we would argue that the stop sign is much more important, and a model should be able to take this into account when doing path planning and even when evaluating its own performance on sign detection. In this next slide, we ask, is the closest or most visible sign necessarily relevant? The sign on the right says right lane must turn right, but we're not in the right lane, so it's not relevant to our path planning. However, the further sign, which is actually smaller and less clear to see at the upcoming stoplight, is a sign that directs the flow of traffic for the lane we are in. Finally, we have another example asking, is the closest or most visible sign necessarily relevant? In this case, we have a speed limit sign which is located in a position that is typically informative to the lane we're in on the right, but the speed limit doesn't apply to our lane since we're on a freeway and that sign is for the exit. So in this case, there's additional information in the sign, such as its color and its location compared to lane markers, that indicate that it's not necessarily relevant to our vehicle. And in fact, if we followed that instruction, we would create an unsafe scene on the freeway. So to this end, we introduce the LAVA dataset for salient sensitive traffic signs. And we point out in the feature set that ours includes a new feature that is not included in other datasets for sign salience. This is a binary marker to indicate whether the sign is salient or not in the given frame. So the next thing we do is we explore the data that we create in this dataset. And as a baseline to decide if we're actually doing any improvement in our learning methods, we start with a trivial classifier, which asks, is the sign located right of center of the vehicle or left of center? If it's right of center, this is where we would typically find signs which are informative to our vehicle path, so we would automatically regard this as salient, and if it's left of center, we'd regard it as not salient. We then improve on this using a ResNet 50 classifier, where we say, instead of using just the location of the sign, let's take the image data itself and look at the sign, noting that the way the sign is shaded or the angle in which it fills its crop, this can indicate things such as the size of the sign, its location relative to the vehicle, perhaps the angle it's located relative to the vehicle, as well as the type of sign, since some signs tend to be more relevant than others or more often classified as salient. To build further off this classifier, we then add some augmentations. We could add the intended vehicle maneuver, such as going forward, turning right, turning left, stopping, then turning, since this would bring out certain signs as becoming more relevant. We can also augment with the location of the sign in the frame, since this can be used to infer the distance to the sign, as well as its position relative to our lane, since perhaps a sign that is far off to the right, too far off and too small is probably for cross traffic or a different scene that happens to be captured by the camera. Additionally, we can add the type of roadway because the roadway type could inform what signs you could expect. On a freeway, you might not expect a school zone sign to appear, and when you're in a residential area, you might not see speed limit 65. So knowing the roadway type could inform whether the sign we're seeing is actually a salient member of the scene. And some of the patterns we find in our scene are shown here. So in general, looking at the middle column, most of the salient signs are located on the right side of the vehicle, as you would expect, which isn't to say there aren't some located on the left, but just as a prior, they're more often on the right, whereas the non-salient signs tend to be more uniformly distributed across the field of view. The location of signs which are salient actually varies based on the scene type, so this joint information could be used to better inform the model. And as we see, the maneuver augmentation actually showed the best performance, reaching near 76% accuracy. In our future work, we would like to perform more experiments and ideally collect even more data. We'd also like to take the sign salience property itself and transform it over time from a categorical, in this case binary, property to something more continuous, so that we can make rankings between scenes or even within a scene as to how important certain signs are and create an order to them instead of just an on-off property. Great. That's our video, and I'm also happy to take any questions for our group too. Thank you.
Okay, thank you for your presentation. Yeah. Of course, the road sign detection is so important there for the autonomous driving environment. Any questions from the audience? Hello? Any questions from the audience? So in this case, I don't know. You want to extract some road signs and then do the classification? Is that true? Or yeah.
I think is your question whether we perform the classification on just the cropped sign?
Yeah, do you do some pre-processing for the like a road sign detection or something? Or
yes, this assumes that we first have an effective sign detector, and then we take the cropped sign and then associated information such as where in the image the sign occurs, and then feed only the cropped portion through the classifier.
So in this case, how sensitive is the method to the incorrect detection of the road signs for the classification? Or?
If there's a sign detector which is not performing accurately, then this method will fail. It relies on as a pre-processing step and a sign detector to be available.
Okay, thank you. Okay, another question is from Addendum. What is the accuracy for smaller sign or sign from distance?
We don't actually have reported separation of results based on the sign distance. That would be a good metric to include going forward. Right now, we treat all signs as equal, whether they're large and in front or further away and smaller. And okay. The sign detection in this case is actually done by hand. So these are hand labeled sign crops, but there are sign detection detectors available in our related work section that we would point the readers to.
Okay, so another question from Addendum. Which sign detector do you use?
Yeah, that was what we addressed here. So if in this case, really each sign, we view each frame and by hand label the corner points that encapsulate the sign. And any state-of-the-art sign detector that we point to in our related works could also be used in this method.
So in this case, then it must be time consuming, yes, for the humans to annotate.
Yes, and that's involved in this presentation here, which is we're really showing the importance of this new data set, and it was time consuming, but we think worth it to give this new attribute of sign salience.
Okay, thank you. Yeah. Okay, so then let's move on to the next talk. It's entitled more or less depending against multiple perturbation attacks on deep neural networks through model ensemble and compression. So the talk will be presented by Hao Chen. So over to Hao. Okay.
It's the
hello.
It's the presenter is around.
Hao Chen, is Hao around?
No, I don't see it. No, I don't think so. No.
Okay, so in this case, we have to move on to the next paper entitled Molecular Depth Estimation using Multi-Scale Neural Network and Feature Fusion. The talk will be presented by Abhinav Sagar. Is Abhinav around? No again?
No again, yeah. Okay, so I think.
Okay, so then in this case, we have to move on to the keynote entitled From Learning-Based Traffic Reconstruction to Autonomous Driving. So our keynote speaker will be Professor Min Lin.
I think we're not time yet. Keynote time is not yet. We have to wait for another 15 minutes. Yeah.
Yeah.
I think I think she is not around yet. So we'll be take a break 15 minutes. We'll be back in just before the keynote.
Yeah, we'll have to take a break for 15 minutes. Then we will start from 6 o'clock in the UK time.
Yeah.
Yeah. Okay.
Okay. Thank you.
Okay. Thank you. Yeah. For your understanding and patience. Yeah.
Hello and welcome back. I think I'm still waiting for Professor Ming to join. I'm not sure whether she is having some difficulty. She did confirmed. She did uploaded the presentations to the to the recorded talk. I'm not sure whether any trouble in accessing.
Do you have any number to call or?
No, I don't have any numbers. That's why I'm looking into it. So maybe let me log into
So email.
to the things. Schedule. No, she uploaded her presentation, isn't it?
Maybe Rohan knows something about her availability.
Not really. I haven't been in touch with her. I can email her, I guess.
I emailed her as well. I'm just waiting. I do not have a direct number to call because
Send a note to Dinesh.
Yeah, let me do that.
But otherwise, I think her recorded video, is it accessible to you, Professor Behra?
yeah, that's why I'm trying to access it. So Young Wai, did you manage to access, isn't it?
To what?
Through the WACV, the
Program?
Program, yeah, the recorded video.
Yeah, in that case, we just have like 4 videos for the 4 accepted papers. Nothing else.
But the keynote also they have uploaded as well.
I couldn't. Let me have a look.
When I access it, it just showing me the talk, but they are inside. I'm not able to see. No, I cannot able to access the videos.
I sent them a note anyway, so
I did send the email as well, so I'm not sure whether she did mention she will be somewhere else and she wants to do afternoon and in Maryland time. That's why I put into the towards the end. She requested me to put afternoon time, so I put in towards the end, which is why.
So Ardendu, one last suggestion I can think of is if you have email for Terry Bolt, he is, I think, the general chair for WACV.
Yeah.
And maybe Terry has access to the video.
Okay, I'm going to, thank you for this suggestion. Yeah, I'm going to do that. we are going to wait for a while. I wrote emails to a few people, and let's wait for a few minutes. No, if nothing going to come out, and then that's the last presentation anyway. We'll conclude the workshop. I think that's the best way to move forward. Okay, I think welcome back, and it is looks like we need to now we try to find out from the list of recordings. It seems that in the recording list also that keynote space is not there, but I do remember we got the email from Terry that she has uploaded the recorded talk. But in the list, I don't see. In the list also, I don't see any keynote recorded in that list they sent to us. And we sent email to Terry as well as Ming, Professor Ming. I think haven't heard anything. Rather than no, where people are waiting. We already 15 minutes past. I would kind of conclude this workshop that. Now, thank you very much as joining us for this workshop from organizers like my colleagues and from different parts of the world, from the keynote speakers from different part of the world as well, invited speakers which are excellent early career researchers. We saw some of the excellent early career researcher presentations, and we can see how the research in these directions moving forward. And there are very interesting insights from traffic condition in unstructured, which covered by Professor Jawahar and as well as Rohan, and the structure scenario in the developed countries, different data sets and things are available, and the insight of the history of the development, these autonomous vehicles, now what Professor Trivedi mentioned about from 80s, and then 2000, 2010 to 15, and then now how we are looking forward into more intelligent and smart in the future with advancement of various sensors from radar, lidars, now all cameras and onboard real-time processing things. Things are moving in right directions. However, we are still far away from the realizations of this kind of technology in a real world scenario where unstructured or the scenario where autonomous vehicle can't take the decision in a perfect, idealistic way. So still we saw some presentations on the first presentations from Dr. Jain, who is an entrepreneur of developing different technology in an industrial scenario, how this technology is maturing up, but still we are not there yet. So looking into all these different angles, we are doing into the same, we are borrowing techniques from the hardware, control mechanisms, AI, vision, machine learning, and trying to come up with an integrated technology to make this the autonomous vehicle or futuristic vehicles to be more practical or more feasible in a real world scenario. So thank you again very much for this joining and contributing. And I'm pleased to say that we are looking forward to take this workshop forward as well. It's not that it's a one time. To be honest, I'd just like to be very honest opinion. When I started this kind of idea at the beginning, I wasn't sure about attracting researchers and early career as well as experienced researchers in this domain, but it turned out to be, it is pleasure and it is everybody's contribution and interest which make this kind of workshop quite successful. And as far as it's planned, we will take this workshop into the next level. Maybe next year we'll target either ECCV or this year ECCV or CVPR in the next year. That's the kind of a target we are looking into it, and then develop from here. Yeah. Any suggestions or anything how to improve or what we could do better in future, is most welcome from all of you.
Well, congratulations from my end. I'm really very happy that you went ahead and put together a great team of collaborators from at least 2 different parts of the world. I see a lot of people from England as well as from India, in the organizational thing. I think you also got some support from some joint program between two governments, I guess. So that is great. I certainly think that there is so much need for what you are bringing out in terms of hazards, perception, and as we saw, things related to unstructured things. And in my mind, really structure and unstructure is in the mind of the beholder. The key idea would be really that there is always uncertainty, and there is always something which happens that you are not expecting. And those things can happen on highways, in structure, out of structure. And what we really want to make sure is that in all of those situations, things should be safe. And certainly we don't want to kill people with the things that we are involved in developing. I think it's like things that people who are in medical field, when they are introducing new vaccines or new medicines, there is such a careful protocol that people follow in making sure that we make this progress in a very systematic, carefully guided by people who are not just technology pushers like me, but really those who are putting their lives on the line, like just general community people. And that is not happening in the field. I think we are really, as all of us are in some level excited by the types of things that we are making, but unfortunately people who are profiting from it are not necessarily well aware of the risks, and people die. I have interacted with families whose members have unfortunately been really victims of this autonomous mode operation of some of these vehicles. And as soon as you connect with individuals who are gone, who were so excited about their own autonomous mode vehicle that they have put their faith in, you realize that this is no joke. Now, fortunately, there are people like you who are aware of it and who are providing a platform as well as, in some sense, a direction where more work needs to happen. And I certainly would support everything that you want to do in the community that you mentioned, ECCV, ICCV, CVPR, and all that. But I also think that it would be good to broaden our engagement, and we should reach people who are in human factors. We should reach people who are in intelligent transportation area, because sometimes every discipline or every little subfield, they may not understand fully what are the challenges that people who are like us, who are developing technology, are aware of it. So at least nothing but some kind of a cross-fertilization is always useful. I think we have been engaged quite deeply with Intelligent Transportation Systems Society, and they have started regular workshops at their Intelligent Vehicles Conference. And thanks to, again, very bright, energetic, enthusiastic participants, colleagues from India, like Professor Ayesha Chaudhary and Professor Sridevi Indu and others, along with Jawahar and others, they are doing this thing. Generally, it is in the summertime. And I think it would be good that we all, in some sense, become members of efforts which are, in some sense, sometimes not properly recognized by all different segmented societies. But challenges are what we all love. And it would be always a great idea to bring in younger, brighter people from all areas to help us out. I think the great thing that developing countries provide is clearly ability to look at some of the edge cases. But at the same time, I think I don't want us to say that people who are in probably high economic index societies, like what United Nations would call, they are not going to die. In fact, they are dying. Unfortunately, not everything is reported. And it's not the death, but I know people who have driven these things and they've returned that car because after a few months of it, they just lost trust in that. And these are people who are Parkinson's patients, who are people who really, I think, can be helped with the types of things that we do if we properly convey to them the limits of the operation and what we cannot do and what we can do honestly. And I think our discipline and our platforms like you are doing are wonderful to let people have somewhat of a fair assessment that they can make. I have been extremely skeptical about reading the business releases and venture things. I have been consultant to some of them, and it's unusual to see that they say that we want to do these things before any regulations come on board. And I think I see their angle that they want to go IPO or go into merger as soon as possible, but I think that is in some sense dangerous. So that's my point of view. All the best wishes to all of you. And it's great to see how far we have come. And I'm confident that it's just a matter of time that many of these hard problems will be solved. And we will minimize loss of life and tragic things that we are reading, but not necessarily getting it registered by people who are in the know of making these things available to people without proper evaluations and assessments. Okay.
Okay, thank you very much. And thank you for the suggestion about involving wider community. We'll take into account those wider community as well. Yeah. Anyone else?
I think one question I probably would like to ask is about whether we are too picky for such kind of like autonomous driving systems. And if we require 1 in million, some kind of like a probability, yes, for some failures, then probably yes, it's just the requirement is too strict. For the humans, probably we've got a much higher like probability yes, for mistakes, for some like accidents. So then in this case, probably it's more about like something like insurance essentially. And the question is whether the industry is ready to insure like the automated cars, vehicles or something. So essentially it's about the probably either some kind of like legal issues or about how to classify the like responsibilities for the failures, either to the humans or the car owners or the companies or whoever. Yeah. So once we know the responsibility of such kind of like failures or accidents, and then probably it's more persuasive as for the public to adopt, and then that would really provide some kind of like motivation to develop such kind of like techniques. Indeed, I think I'm also like skeptical about whether the technologies are really ready by like 2028, for example, for all different kinds of like issues surrounding the autonomous car or vehicles or whatever. So indeed, I think I don't know whether that's the point missing or largely overlooked by the community. Essentially, it's about the legal issues for such kind of like automated vehicles or something. Of course, I here really feel grateful to all our keynote speakers. They do provide a comprehensive like a review and then coverage or some kind of like summary of the techniques, developments, or very kind of like issues along in the past, like let's say 40 years, 30 years, something. And also I feel grateful to all the like invited speakers and the contributed, all those who focus more on like the technical details of the technology development or the probably low level, the support for the development of the autonomous vehicles. But of course, such kind of like a low level, like technologies are critical. They provide a foundation for the developments. And finally, I would like to express special thanks to Adendo, who initiated the workshop and then who brought all the people around and then finally created this, I think, is exciting program. And I'm sure it really helped different like researchers to get familiar with the ideas and then state of the art and where also the possible future directions. And of course, here we do find some other like issues, just like such kind of like legal issues, or whether the technologies are really mature enough in 10 years time or 20 years time, and then whether we really require like a 1 in a million like probability for some like failures or something like that. So that would really create some new opportunities for us to do research, to do the development, and then move forward of the field. Okay, so thank you all for this exciting program and then this successful workshop. Finally, thank you so much for your attendance and contribution to this workshop.
Okay, so thank you and have a nice rest of the day, and we'll be keep in touch. Yeah, okay, thank you.
Okay, thank you so much.
Thank
okay,
you.
bye-bye.
Bye.
Bye.